8 congruent equilateral triangles, each of a different color, are used to construct a regular octahedron. How many distinguishable ways are there to construct the octahedron? 2 colored octahedrons are distinguishable if neither can be rotated to look just like the other. Okay, so we're going to need to first figure out what is going on, what is being asked. So you've got this octahedron right here, and they are coloring each side a different color. There's 8 sides, right? 1, 2, 3, 4, 5, 6, 7, 8. And each of those sides is an equilateral triangle. And they're basically asking, when you color each side a different color, how many ways of doing that? So one approach to doing this question is by putting a cube inside that octahedron as shown in that diagram. And the vertices of the cube right here, 1, 2, 3, 4, 5, 6, 7, 8, all those vertices will basically be touching each of the 8 faces of the octahedron. And you can see that. And therefore, what we really just need to do is figure out how many combinations are there. So let's go through this. First and foremost, you have 8 colors. All right? Let's pick one vertice, so I'll pick this one right here. And I'll call that 1. And that one is fixed. So vertex 1 is fixed. And for vertex 1, choose any color of the 8. And then now we have to choose colors for the remaining 7 vertices. 1, 2, 3, 4, 5, 6, and then one that we can't see right now. It's behind. So how do you do that? Well, using probability, combinatorics, whatever. There are 7 times 6 times 5 times 4 times 3 times 2 times 1 possible combinations of the remaining 7 colors. And that equals 5,040. But is this the answer? Well, none of the answers are 5,040. And the reason is because this triple counts the total number. And I'll explain why a triple counts. If you have a vertice right here, like that, and this is fixed, the vertices that are joined to it are this one, and this one, correct? So let's label them. Let's say this is 2, and this is 3, and this is 4. Those 3 vertices can be rotated, and once they are rotated, they result in the exact same orientation or situation. So basically we've triple counted because the 3 vertices are joined by the edges of the first vertex, right? Right there, you've joined all 3. And when you rotate them, you get 3 rotations for each of these situations. For example, so if you rotate the first one, which is 1, 2, 3, 4, just like that, it can become 1, 4, 2, 3, or 1, 3, 4, 2, like that. So each of these basically has 3 orientations that make it exactly the same. And they use this specific word here, distinguishable. And that means that octahedrons are distinguishable if neither can be rotated to look just like the other. So for these 5,040, we've triple counted because there's 3 that will always be non-distinguishable, right? They'll be the same if you can rotate them. So therefore, since we've triple counted and we've explained why, this number has to be divided by 3. So 5040 has to be divided by 3 to get the distinguishable octahedrons, and that is 1680. So therefore the answer to number 25 is E. So the answer to number 24 is D. Consider sequences of positive real numbers of the form x 2000 y ... in which every term after the first is one less than the product of its two immediate neighbors. For how many different values of x does the term 2001 appear somewhere in the sequence? Okay, so we've got x, 2000, y, and then we keep going like that. And they're saying that there's a fundamental property that every term after the first is equal to one less than the product of its immediate two neighbors. So that means if we take 2000, 2000 is equal to one less than the product of its two neighbors, like this. Okay? So I hope you understand that. Every term after the first is one less than the product of its two immediate neighbors. Okay? So, let's go with that. This is term 1, this is term 2, this is term 3, and we'll try to find a bunch of terms here. Hopefully we'll see a pattern, and that's usually the type of scenario in these kinds of questions. I'll try until T7 and then I'll run out of patience. All right, so for the first one, I've got bring the 1 over. 2001 is equal to xy, and therefore y is equal to 2001 over x. Okay, so let's try to make this neat. Let's not make it messy. Let's use different colors. X is fixed as x, all right? 2000 is fixed as 2000, but y is 2001 over x. All right? Okay, so far so good. So that was T3 that we just found. Okay, now let's figure out T4. How do we figure out T4? Well, according to our formula, every time you have a term like T3, it's equal to one less than the product of its two neighbors. So its two neighbors are T2 and T4, like that. Okay? So that means T3, which we already figured out is 2001 over x, is equal to T2, which is 2000, times T4, minus 1. So do a little bit of algebra here, and you're going to get 2001 over x plus 1 is equal to 2000 T4, like that. So this looks like 2001, common denominator is x, like that, and 2000 T4. So T4 is 2001 plus x over 2000x. Okay? So where do I squeeze that in there? Maybe I'll need a little bit more space. So I've got 2001 plus x over 2000x for T4. So the next one we are going to figure out is T5. So we were going to have to go T4 is equal to T3 times T5 minus 1, like that. T4 is 2001 plus x over 2000x is equal to T3, which is 2001 over x, T5 minus 1. So you're going to have 2001 plus x. If you add the 1 to that side and get a common denominator, it'll be 2000x all over 2000x, like that. And this equals 2001 over x T5. So this looks like 2001 plus 2001x over 2000x times x over 2001 is equal to T5. All right. And let's see, does this simplify in any way? If you factor the 2001, you get 1 plus x, and x over 2000x and 2001. Okay, great. The 2000s go and the x's go. So T5 is left with just 1 plus x over 2000. All right. So 1 plus x over 2000. Moving right along. Now we get to, what are we up to now? We have to find T6 next, right? So T6 we will have to use T5 is equal to T4 times T6 minus 1. T5 is 1 plus x over 2000. T4 is equal to 2001 plus x over 2000x. And T6 minus 1, like that. So we'll bring the 1 over and get a common denominator, which will be 2000, like that. And then this is 2001 plus x over, this is a 2000, 2000x, T6. So we've got 2001 plus x over 2000 times cross multiply 2000x over 2001 plus x is equal to T6. And looks like that, oh, this is great. This actually simplifies to just x. All right, great. So I am going to get a pattern. One more, T7. I know this is torture, but it's okay. So one more and we got, let's see, we're trying to find T7, right? So T6 is equal to T5 times T7 minus 1. X, T5 was, what was T5? 1 plus x over 2000. T7 minus 1. So you got x plus 1 is equal to 1 plus x over 2000, T7, and therefore T7 cross multiply 2001 plus x, so T7 is equal to just 2000. Perfect. So we indeed have a pattern, okay? It's going to repeat. X 2000, 2000 over x, 2001 plus x over 2000 x, 1 plus x over 2000, and then it'll be x 2000, and it'll just keep on going like that. Now, what are they asking in the question? For how many different values of x does the term 2001 appear somewhere in the sequence? What is the value of x if we set these terms equal to 2001? All right. We can figure that out. So the first one, if we set it equal to 2001, we're done. So that pretty much takes care of the first one. How about if we let the second one, 2001 over x equal to 2001? Well, that would mean that x is equal to 1. So this is one value, this is another value. How many different values of x does the term 2001 appear somewhere in the sequence? All right. So if we let x equal to 2001, the term 2001 will appear in the sequence. It will be T1. If we let x equal to 1, this T3 becomes 2001, and therefore the term 2001 will appear in the sequence. All right. So I hope you understand. So again, T4, we got to let that equal to 2001. Probably have a little bit more algebra here. So we got 2001 plus x is equal to 2001 times 2000x, like that. 2001 is equal to 2001 times 2000x minus x. Factor out the x and you'll get 2001 times 2000 minus 1, and therefore x is equal to 2001 over 2001 times 2000 minus 1. Okay, so this is another value of x for which the term 2001 will appear in the sequence. So that's a third value. And we've done T1. T2 is fixed, so we can't do T2. We've done T3, we've done T4, and let's see what we get for T5. So T5 is 1 plus x over 2000, and we set that equal to 2001, and therefore 1 plus x is equal to 2001 times 2000, and therefore x is equal to 2001 times 2000 minus 1. So here is a fourth value. So when x is equal to 2001, this expression, T1, will become 2001. When x is equal to 1, T3 will become 2001. When x is equal to this big long number, T4 will become 2001. And when x is equal to 2001 times 2000 minus 1, T5 will become 2001. So we've got 1, 2, 3, 4 values of x that make the terms equal to 2001. And therefore the answer for number 24 is number 25. The non-zero coefficients of a polynomial p with real coefficients are all replaced by their mean to form polynomial q. Which of the following could be the graph of y equals px and y equals qx over the interval minus 4 to 4 for x? So polynomials like p are of the form a x to the n plus b xn minus 1 plus c xn minus 2 plus ... all the way to z. And what they're doing is they're creating a second polynomial where all of these coefficients, a, b, c, all the way to z, are replaced by the mean. So I'll write m for mean. So now you have x to the n plus m x to the n minus 1 plus m x to the n minus 2, like that, all the way ... plus m. Move this over a little bit. All right, so that is what they're doing in the question. Now, what is the mean? The mean of what? The mean of the coefficients of p. So the coefficients of p are a, b, c, all the way till z, right? You have to take those and make a mean. So you have to take the mean of these coefficients. And how do you take the mean or the average? You add them all up and you divide by the number. How many coefficients are there? Well, there's n all the way down to 1, and then there's one final one right here, z, because z doesn't have an x with it. So that means there's n plus 1 coefficients in p. And that is the mean. That is what m is. It's the sum of all the coefficients divided by the number of coefficients, and the number of coefficients is n plus 1. All right? So now we have to somehow figure out the graphs of p and q. How do we do that? Well, there are several ways of going about this question, but I want you to concentrate on something pretty cool, I think, is that what are each of these going to look like when x is equal to 1? So find P at 1 and compare it to Q at 1. All right? So if we were to just multiply this, it will be like this. Is equal to A plus B plus C dot 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 plus C. All right? So here we go. Now let's look at P at 1. Why did I choose that? What's special about 1? Because if X is 1, all the X's essentially disappear. They don't disappear in the sense that they make everything disappear. Just the X's would disappear. Watch what happens. P at 1 becomes A, 1 to the power of n, plus B, 1 to the power of n minus 1, plus C, 1 to the power of n minus 2, plus dot dot dot, all the way to Z. And this just becomes A plus B plus C. You see what happened there? All the X's go away. So P at 1 is equal to A plus B plus C all the way to Z. You see how it made it kind of this essentially the sum of all the coefficients? And the sum of all the coefficients we just did up here. It's m times n plus 1. All right? Now let's do the same thing for Q. Let's find Q at 1. When X is 1, what is the value of Q? Well, it will be m times 1 to the power of n plus m times 1 to the power of n minus 1 plus m times 1 to the power of n minus 2 plus dot 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 plus m at the very end. This just becomes m plus m plus m all the way till m. Well, how many m's are there? There are n plus 1. N plus 1 m's, correct? Because you have n minus 1, n minus 2, all the way down to 1, and then you have one final one. So you have n plus 1 m's. So to get the sum, you would just go m times n plus 1. And do you see something similar? That's the same. So that basically means that P at 1 is the same at Q at 1. They're equal. So what does that mean graphically on a graph? It means that when x is equal to 1, the graphs of P at x and Q at x intersect, correct? They have the same value. So that is the heart of our question right there. We have to look at those graphs, look at x equals 1, and see which graphs intersect at that point. So let's take a look. A, when x equals 1, this is 1, right? They don't intersect. How about B, when x equals 1? It looks like they do, right there. So let's keep that one. C, when x equals 1, they don't. D, when x equals 1, they don't intersect. And E, when x equals 1, they don't intersect. So by process of elimination, and the only one that matches our findings is B for number 25. Let f at x equal the square root of ax squared plus bx. For how many real values of a is there at least one positive value of b for which the domain f and the range of f are the same set? So f at x is equal to the square root of ax squared plus bx. And we have to look at three scenarios. We have to look at the first scenario, which is when a is 0. The next scenario is when a is greater than 0. And finally, when a is less than 0. So first, I will start with this scenario right here. If a is equal to 0. If that is the case, then our expression becomes f at x is equal to bx under the square root sign. Okay? And then therefore, for all positive values of b, the domain, which is all the possible x values, is that x has to be greater than or equal to 0, right? Because you can't take the root of a negative number And then the range, which is all the possible y values or all the possible values for f of x, is that that's also greater than or equal to 0, because f of x is the square root of a number, so it's always going to be positive or equal to 0. So in this case, as you can see, the domain and the range are the same. So that fulfills the criteria of our question. For how many real values of a is there at least one positive value of b for which the domain of f and the range of f are the same? We found one. When a is 0, for all positive values of b, the domain and the range are the same. So there we go. We've got one value for a. Let's see how many more we can get. So the answer to this question cannot be 0 because we've got at least one value, but we obviously have to figure out if we have more than one or if we have infinitely many. Now I will turn my attention to a greater than 0. Now since a is no longer 0, we can put in the value of the full expression, which is f of x is equal to ax squared plus bx. All right? Because a is no longer equal to 0. Now, first, let's figure out the roots of this equation. So if we set it equal to 0, we'll get ax squared plus bx, all in the square root sign. Square both sides, and you'll get ax squared plus bx. Factor out an x, you'll get x, ax plus b, like that. And therefore, x is equal to 0, or x is equal to minus b over a. These are the roots. So now let's turn our attention to a is greater than 0. If greater than 0 is our situation for a, then we can draw this on a graph. And let's label all roots. This is x, this is 0, and minus b over a is going to be somewhere here. How do we know that? Well, because recall, the question tells you that b is positive. And if b is positive and a is positive, that means minus b over a is negative. And that's why I was certain that it belonged in that quadrant. So if we have a graph of this expression, the graph, if you notice, this is just a quadratic, so it's basically like a parabola, but you're taking the square root. So if it was just a parabola, it would kind of look like this, right? Like that, something like that. But because this is a square root, y can never be less than 0. So this part of the graph is not going to be there. So now let's talk about the domain and range. The domain, of course, is all the x values. So x from this graph, you can clearly see, has to be less than or equal to minus b over a, or it can be greater than or equal to 0. And the range, which is the possible values of y, or f of x in this case can only be greater than or equal to 0. And as you can see here, the domain and the range are not the same. And that was one of our criteria. So that means basically that for a greater than 0, this will never hold true. The domain and range will never be the same. So none of our a values will be greater than 0. So now we move on to the last one, which is a less than 0. And remember that b is positive. They tell you that in the question. And if you remember, our roots were 0 and minus b over a for x. We found that out earlier in the question, right here. And therefore, we can now draw a graph. But where do I put my minus b over a in which quadrant? B is positive and a is negative. So that means that minus b over a is going to be a positive number, correct? Because b is positive and a is negative. So you'll have negative over a negative, which is positive. So minus b over a will be in this quadrant. It'll be somewhere here. And then 0, of course, is here. And then remember our initial equation, f at x, is equal to ax squared plus bx, all under the square root sign. A is negative now. So this will be kind of like a parabola, but because the coefficient a is negative, it'll be a parabola pointing down. So it'll be something like this. So that will be sort of like what it looks like. Now let's look at the domain and range of this. The domain, of course, is all the possible x values. And it looks like the domain is going to be between minus b over a and 0. Why? Because remember, f at x is always positive. Always positive. So that means that this part of the graph cannot be there. That part of the graph. So that means that these are pretty much the boundaries of x. 0 and minus b over a. Okay? Now we need the domain and range to be the same. So that means the range must also be the same. If we can find an a that makes the range the same as the domain, we will find another value of a. So basically what we're saying is we are most interested in this point right here. That point. What is that point? If it is minus b over a, that means that our range is also between minus b over a and 0. That is what we are chasing now. So how do I figure out the x value of when y is equal to minus b over a? So I guess what I'm asking is, when you have x right here, that is when f at x is equal to minus b over a. But what is the x coordinate here? Well, by the symmetry of this diagram, it's basically half the distance from there to there. So if from there to there is minus b over a, this will be minus b over 2a. When x is minus b over 2a, y will be minus b over a. And that is what we are going to set, and that will allow us to figure out the value for a. So here we go. We've got f at x is equal to ax squared plus bx, all under the square root sign. Our x is going to be minus b over 2a, minus b over 2a, all squared, plus b minus b over 2a, all under the square root sign. And f at x is going to be minus b over a, this right here. This will allow us to figure out a value for a. So let's concentrate on this, what's under the square root sign. We've got a b squared over 4a squared, and then we have minus b squared over 2a, like that. And then looks like we will get a common denominator of 4a squared, so this has to be multiplied top and bottom by 2a, like that. So this will be ab squared minus 2ab squared all over 4a squared. And then this looks like ab squared minus 2ab squared is negative ab squared all over 4a squared. And at least one a cancels from the top and bottom. We're left with minus b squared over 4 a, like that. Square root. And we can kind of fiddle around with this. We can put the negative below like that. And then just kind of split up the root sign. And that's about as far as we can go. And this is all equal to minus b over a, like that. So the square root of b squared, of course, is just b. And then we're left with the square root of minus 4a squared, like that. And this is minus b over a. The b's cancel, and we're just left with minus 1 over a is equal to 1 over minus 4a. And then we can flip this. So we'll just get minus a is equal to the square root of minus 4a. And then if you square both sides, you'll get a squared is equal to minus 4a. Correct? And then you can divide both sides by a, and that just leaves with a is equal to minus 4. And there you have it. A is equal to minus 4 is what allows the domain and range to be the same. So how many values of a did we get? We initially got, at the very beginning, we got one value of a here. A is equal to 0. And then when a was greater than 0, the domain and range cannot be equal, so no values there. And when a was less than 0, after all this, we were able to get a equal to negative 4. So that's our second value. So a equals 0 and a equals negative 4 are the two values that allow the domain and range to be the same. And therefore, two values is the right answer, and 25 is therefore C. For each integer n is greater than or equal to 4, let an denote the base n number 0.133, all repeat to base n. The product a4, a5, ... to a99 can be expressed as m over n factorial, where m and n are positive integers, and n is as small as possible. What is the value of m? So first, let's explain what they mean when they write 0.133 repeat n. Well, what do they mean by that? Well, I'll give you an example. Let's say n is equal to 10. That means this is base 10. Correct? So this basically becomes 0.133. It just keeps repeating, right? That's what that line means. So this would basically be, written in base 10, 1 times 10 to the negative 1 for this digit, plus 3 times 10 to the negative 2 for this digit, plus 3 times 10 to the negative 3 for the next digit, plus 1 times 10 to the negative 4 for that digit, plus 3 times 10 to the negative 5 for that digit, and then 3 times 10 to the negative 6 for the sixth digit, and so on. It just keeps on going like that. So they're saying that a to the n is this number to the base n, where n could be 4, 5, all the way up till 99. All right? So we have now a to the n is equal to 0.133, all repeat, n. And this is base n. Okay? So this basically becomes 1 times n to the negative 1 plus 3 times n to the negative 2 plus 3 times n to the negative 3 plus 1 times n to the negative 4 plus 3 times n to the negative 5 plus 3 times n to the negative 6, and so on. Because now n could be one of many numbers. So this basically means this is 1 over n plus 3 over n squared plus 3 over n to the power of 3 plus 1 over n to the power of 4 plus 3 over n to the power of 5 plus 3 over n to the power of 6, and so on. All right, ... Keeps on going. So now we have to do a little bit of fancy manipulating. And that's the challenge of this question. I'm going to multiply everything here, both sides, by n to the power of 3. N to the power of 3. This whole thing. I'm allowed to do that because if I do something to the right side and I do something to the left side, that's perfectly allowable. When I do this, what happens? Well, on this side I get n cubed times an. But watch on this side, this becomes n squared. This becomes 3n. This becomes 3. This becomes 1 over n plus 3 over n squared plus 3 over n cubed plus dot, dot, dot. Now you say, well, what was the point of that? Well, this right here is the same as a to the n. I hope you can go back and convince yourself of that. And that is very helpful because now we can get rid of the dot, dot, dot and just put a to the n like that. So here you go. We've narrowed it down to this. Okay? So now let's work with this. This now, if you put the an on one side, we'll get n to the power of 3, an minus an is equal to n squared plus 3n plus 3. Okay? Factor out an an, and you get n to the power of 3 minus 1 is equal to n squared plus 3n plus 3. And therefore an is equal to n squared plus 3n plus 3 all over n to the power of 3 minus 1. All right? Take a second there to digest that. Now we continue with a little bit more of our magic. I'm going to multiply top and bottom here by n, like that. Okay? If I do that, I get the following. an is equal to n cubed plus 3n squared plus 3n. And on the bottom, I'll just leave it in factored form like this. And now one final step, one final magic step. I'm going to add 1 and subtract 1 on the numerator. If I do that, I can factor these terms, and they become n plus 1 to the power of 3. And then don't forget the final minus 1 like that. All over n times n to the power of 3 minus 1. Okay? So this is basically where you have to get to, this stage. I know that's difficult. I would agree. Anybody who says that this is challenging. Well, it's number 25 on the AMC 12, so of course it's going to be challenging. Now let's go back and see what is it that they want. They want this, A4 times A5 all the way to 899, and they want you to show that it can be expressed in the form of m over n factorial. Okay? So let's see here. I've got to show that this basically can be written m over n factorial. And what is that? A4 times A5 all the way to dot, 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 A99. Correct? Let's see if I missed anything. Nope, that was right. A4, A5 all the way to A99. Okay, so what is A4 times A5 times A6 all the way till A99? Let's see what we get using this formula that we just figured out. Well, let's see. A4 would be 4 plus 1, so 5 to the third minus 1 all over 4 times 4 to the power of 3 minus 1, correct? And then you're going to multiply that by A5. A5 using this formula up here is going to be 6 to the power of 3 minus 1 over 5 times 5 to the power of 3 minus 1, like that. Let's just do a couple more. For A6, it will be 7 to the power of 3 minus 1 over 6 times 6 to the power of 3 minus 1, dot, 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 all the way till 99. When it's 99, it'll be 99 plus 1, which is 100 to the power of 3 minus 1. And the denominator looks like it would be 99 times 99 to the power of 3 minus 1. Okay. Now, good thing is a lot of these cancel. So, for example, this cancels with that cancels with that, and everything will cancel. This will eventually cancel with that. And the only thing you're left with on the top is just 100 to the power of 3 minus 1. And you'll have basically all these guys, 4, 5, 6, all the way to 99. So 4 times 5 times 6, dot, 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 all the way to 99. And then you'll have this lone, don't forget about that guy, that's the one that didn't cancel, 4 to the power of 3 minus 1. Okay, so far so good. So the top becomes, oh boy, 100 to the power of 3 minus 1. So I think that's a million minus 1, so 9999, like that. And then the bottom, 4 times 5 times 6, dot, 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 to 99. And then 4 to the power of 3, 64 minus 1 is 63. Okay, we have to somehow show that this is m over n factorial, correct? Well, this looks very similar to a factorial, but we're missing a couple digits there. Well, no problem, I can add them. If I put a 1 times 2 times 3 here, right? That would be helpful. Can I do that? Sure I can. 1 times 2 times 3, as long as I do it to the top. 1 times 2 times 3, like that. Okay? So basically, I just made that to make this whole thing into a factorial. So I made the denominator now 99 factorial. All right? And I still got this 63 here. And the top becomes, oh boy, you got 6 times 999, like that. Okay? Got to do a little bit of math here. A little bit of math without a calculator. So we've got to figure out this whole thing right there. And if you do, you'll find that is 95238 over 99 factorial. Okay, great. I got it in this form. So they want me to figure out what is m. Well, therefore, m is 95238. Right? Let's go see. 95238 is not one of the answer choices. Okay. Well, why isn't it one of the answer choices? Well, they want n as small as possible. So perhaps my n is not as small as possible. Okay. This was my n. All right, so let's see if I can make it any smaller. 95238. How about if I make it 98 factorial and then I take out the 99 and put it there? If I do that and then I take those two numbers and divide them, I will get 962 over 98 factorial, like that. And this is indeed in the form m over n factorial, where n is as small as possible. Correct? Because if you went 97 and 98, 962 is not divisible by 98. So therefore, n equal to 98 is the smallest that you can get for n. So therefore, m is 962. And that means that number 25, the answer is E. Let S be the set of all points with coordinates x, y, z, where x, y, and z are each chosen from the set 0, 2, 1. 0, 1, 2. How many equilateral triangles have all their vertices in S? So the best way to do this is with a diagram. So here's our diagram. We've drawn an xy plane, xyz plane. And basically you've got for x, y, and z, it can be either 0, 1, or 2. So you can only choose between those three numbers as a possible coordinates. And if you do that, you will be able to see that you will create, first and foremost, unit cubes where the vertices are only going to be within one of each other. And that's if you just chose this one or if you just chose those two. First, we'll just concentrate on the unit cubes. So one unit cube gives several equilateral triangles. And this red illustrates one such equilateral triangle. You'll notice that it has a length from there to there for each of its edges. And since the length from here to here is 1, we can easily figure out through Pythagoras that the edge is root 2. So it gives equilateral triangles of side length root 2. Now, how many does it give? If you have a unit cube, how many? Well, each of these vertices of the unit cube will produce 1. And how many vertices do we have in a cube? We have 1, 2, 3, 4, 5, 6, 7, 8, correct? So we get 8. Okay? But how many unit cubes? The whole thing is 2 by 2 by 2. So that's 8, right? So if you have a cube of volume 8, that is 8 unit cubes. And since each unit cube gives 8 equilateral triangles, 8 unit cubes will give 8 times 8, 64 equilateral triangles. All right? But that's just the first part of the question. We also have to take into consideration when you have a full cube where the whole sides are of length 2 each. And the green triangle represents one such equilateral triangle. At this time, we are now drawing side lengths that are much longer, double the length. So instead of root 2, these now have side length 2 root 2. All right? Now, how many of those green triangles can I make? In a very similar way, each of these vertices will produce one such triangle. So there's 8 that will be produced by the big cube. Also, we have large equilateral triangles of side length 2 root 2, 1 per vertice. So we have an additional 8 large equilateral triangles. So we have 64 and 8. So that means 64 plus 8, we have a total of 72. So 72 is our total. 72 is one of the answers, but perhaps we can get a few more. Let's see. Now, what if I chose triangles like this, where they are connected by the midpoints of sides? By connecting midpoints of non-adjacent, non-parallel edges, an additional 8 equilateral triangles can be made, as shown. So we have 8 here, we had 72 here, 8 plus 72 is 80. So the grand total is 80, and therefore number 25, the answer is C. How many non-empty subsets S of 1, 2, 3 until 15 have the following two properties? Number 1, no two consecutive integers belong to S. Number 2, if S contains k elements, then S contains no number less than k. So first, let's try to understand this question. What is the question telling us? Well, let's start with the point 2 first. S contains k elements, then S contains no number less than k. So for example, let's say k is equal to 1. If S contains k elements, that means S contains one element. And S contains no number less than k, so S contains no number less than 1. Well, there is no number less than 1, so it looks like the set will be any of these numbers. All right? So from those numbers, you can choose any of them and choose one number as your set. All right? So for example, if I chose 1, that's it. That's my set, because I have chosen k to be equal to 1, so that means the set contains only one element, and I can choose from any of these numbers because I didn't have to eliminate any of these numbers, since when I say that the set contains no number less than k, well, there is no number less than k because k is 1. So for the first scenario, k equals 1, how many ways can I choose a number? Well, it's from 15 numbers, choose 1. And I hope you know how to do this. If you don't, I'll just remind you it's 15 factorial, 15 minus 1 factorial times 1 factorial. And this is equal to 15. Okay? So there you go. That's for k equals 1. Now when k equaled 1, what did we have for n? And n refers, in my example, to how many numbers do we have to select from? Well, we had the full 15 because we didn't eliminate any. All right? So that takes care of k equals 1. Let's go to k equals 2. All right, same kind of story, k equals 2. And before I get to k equals 2, let me just talk about point number 1 when k is 1. No two consecutive integers belong to S. Well, we only have one integer in there, so there's no real issue with regard to consecutive integers. It will become an issue when k equals 2, and that is what we're going to talk about now. So when k equals 2, the set now contains two elements, right? K is 2. And S cannot contain any number less than 2. So that means my set cannot have the 1 in it. So I can only have 2, 3, 4, up until 15. All right. So now my set has two numbers in it. Okay? I'm going to choose one number, and then I'm going to choose another number. And now I have to be concerned with my first rule, which is that I can't choose consecutive numbers. Okay? So that's very important. So, how do I do that? Well, let's do it in the simplest way possible. I'll choose 2, and then I can't choose 3. Why? Because remember rule, no two consecutive integers, so I've got to choose maybe the 4. All right, that is one way of doing it. That is according to the rules of the question. Now, notice, after choosing my two numbers, when two numbers are chosen, we skipped over one number, correct? The one number we skipped over in this case was 3. So we chose two numbers from really the remaining 13. from these 13 numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So mathematically, what that really means is that from 13, choose 2. And 13 choose 2 is equal to 13 factorial over 11 factorial over 2 factorial. And that is going to be equal to 78. All right? So I hope you get the hang of it. And just to be complete, what was n in this case? N I'm representing as the number of numbers in my set right here. Well, I believe in total it was 14. Okay? So, hopefully you're getting the hang of this. Let's keep going here. So now let's let k equals 3. If k equals 3, remember we can't have any number less than k, so we can't have a 1 or a 2, but we can have everything from 3 to 15. So let's write n in here. How many numbers are there that I can choose from this time? It looks like 13. Okay, so my set now is going to have 3 numbers in it. So I've got to choose 3 numbers. All right, let's do this in the simplest way. Choose a 3, 3 goes here. Can I choose a 4? No, because I cannot have digits that are consecutive, right? That's one of the rules. No 2 consecutive integers can be chosen. All right, I can choose a 5. That's perfectly fine. Can't choose a 6, but I can choose a 7. All right, this is just one way of choosing it. And in a very similar way, when k equals 3 numbers are chosen, we skipped over 2 numbers. And those numbers in our example was 4 and 6. We skipped them over, right? We can't choose those because it would violate the terms or rules of the question. We therefore chose 3 numbers from the remaining 11. So mathematically, that means from 11, choose 3. And 11 choose 3 is 11 factorial over 8 factorial over 3 factorial. And the numerical value for 11 choose 3 is 165. Okay? So far, so good. Hopefully you're following. And the good news is we've only got 2 more. And then our rule ends. And without going through this entire thing, I think by this point you get it. So for k equals 4, n would equal 12. We only have 4 to 15 as our choices. And we're going to choose 4 numbers this time. And in a very simple way, we can choose, say, 4. Can't put the 5. We've got to skip over that. We can put a 6 here. Can't put a 7. But we can put an 8. Can't put the 9, but we can put the 10. So we skipped over the 5, the 7, and the 9. So when k equals 4 numbers this time are chosen, we skipped over 3 numbers. It was the 5, the 7, and the 9 that we skipped over. So essentially, we chose 4 numbers from the remaining 9 numbers. And those 9 numbers are, of course, 4, 6, 8, 10, 11, 12, 13, 14, 15. And therefore, mathematically, that is from 9, choose 4. And I'll just give you the numerical value. It's 126. K equals 5. This is the last one, by the way, just in case you're wondering. K equals 5. This time we have numbers from 5 to 15 as our choices. And in a very similar way, we are now going to choose 5 numbers. And we can do them in lots of ways, but I'll just give you one. Let's say I chose a 5 here, 7 here, 8. Can't choose the 8, right? Because that's consecutive. 9, 11, 13. That's all fine. But then if I did that, I had to skip over the 6, the 8, the 10, and the 12. So when k equals 5, we chose, of course, 5 numbers this time for our set. And we skipped over 4 numbers, 6, 8, 10, and 12. So essentially what we did was we chose 5 numbers from the remaining 7. And those 7 numbers were 5, 7, 9, 11, 13, 14, 15. So mathematically that means from 7 choose 5, and that is equal to 21. All right, how about if k equals 6? Well, the good news is we don't have to do that. Why? Well, let's see. If k equals 6, our set is between 6 to 15 in terms of what we can choose from. And there's no way for us to make rule number 1 work. Watch what happens. Let's say I put the 6 here. Can't put a 7, put the 8 here. Can't put the 9, put the 10 here. I can put a 12. I can put a 14. And then there's nothing. I can't choose any number now. If I put a 15, I violate the rule. If I put any other number in here, like let's say 11, well, I've got 2 consecutive numbers. So when k equals 6 or greater, k greater than or equal to 6, we can't meet the criteria. So I think we've got it all. We only have to figure it out for k equals 1, 2, 3, 4, 5. So what did we get? For k equals 1, we got 15. For k equals 2, we got 78. For k equals 3, we got 165. For k equals 4, we got 126. And for k equals 5, we got 21. So we've got to add up 21, 126, 165, 78, and 15. And this adds up to 405. So number 25, the answer is E. Call a set of integers spacey if it contains no more than 1 out of any 3 consecutive integers. How many subsets of 1 to 12, including the empty set, are spacey? In this question, what we need to do is figure out how many of these spacey sets there are. But we're going to use a system. What we're going to do is first look at how many numbers are in the set, and then we will figure out how many of those sets there are. So the size of the set will go here, and then we will figure out the number of such sets. Now, I'm going to do this by casework, and I'm also going to show you a formula. Now, the formula you might be able to get on your own, but if you can't, you can also do it by casework. I'll do both. The formula is basically 14 minus 2k. From that, you choose k. So the choose notation, 14 minus 2k. From 14 minus 2k, you choose k. But in case you didn't or weren't able to figure that out, we can do it by casework, no problem. So I've got 1 through 12. And now let's look at the size of the set. Let's say the size of the set is 0. Well, it's an empty set. How many such empty sets do we have? Well, just one, the empty set. Okay, so in our formula, that basically means that my value for k is basically going to be equal to the size of the set. So I'll put that over here. So it became in choose notation 14 choose 0, and that is indeed equal to 1. All right? Now let's go with k equals 1. 1 is my set number. If 1 is my set number, that means the set only has one number in it. So it can be any one of these 12 numbers. It could be a set with just 1, a set with just 2, and so on, right? So there's 12 ways of doing that. That's pretty straightforward. So by casework, I got 12, but if you wanted to use the formula, it would be 14 minus 2, which is 12. From 12, choose 1. And 12 choose 1 is indeed equal to 12. So there you go. Now we get into a little bit more difficult. The size of the set this time is 2. So we've got, let's say, 1 as my first number in that set. What can I use for the second number? I cannot choose 2 and I cannot choose 3. Why? Because they are consecutive integers. 3 consecutive integers, I can only choose one of them. But I can choose any of these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I got 9 choices and any of those are perfectly acceptable. So 9 choices, that gives me 9 possible. 1, 9, 1 times 9. It can be 1, 4, 1, 5, 1, 6, and so on. Okay? So if 2 is my next set, in terms of the first number in the set, then can I choose 1? No. Can I choose 3 or 4? No. But I can choose any of these guys. 1, 2, 3, 4, 5, 6, 7, 8. So now I can choose any of 8 numbers. So that gives me 8 possible sets where 2 is involved. And for 3, if 3 is one of my set numbers, I can't choose this guy or this guy or this, but I can choose any of those numbers. 1, 2, 3, 4, 5, 6, 7. So for 3 in my set, I've got 7 possibilities. For 4, it gets a little tricky because for 4, I can't use this, or this. This one I can use, but I've already counted that. Remember? 4, 1 is the same as 1, 4, and 1, 4 is one of these guys. So the only new ones that are left for 4 are these ones. So there's 6 of those. Similarly for 5, it's the same kind of story. I can't use that, or that. 5, 2 is valid. 5, 1 is valid, but 5, 2 and 5, 1 I've already used. 1, 5 is up here, and 2, 5 is already one of these guys. So the only new ones are these ones, and there's 5 of those. And in a very similar way, you'll see that for 6, there's 4. For 7, there's 3 new ones. For 8, there is 2 new ones. And for 9, there's 1 new one. And then after the 9, there's 0. So this is what we have to add up. So 1 plus 2 all the way to 9 is 9 times 10 over 2, which is 45. So 45 is the answer there. And if you use this K notation, this choose notation, for K equals 2, that becomes 10 choose 2, and 10 choose 2 is equal to 45. Okay, so in both ways, this works. Now let's move to 3 as my size set. So let's say I've got 3 as my size set. Now, how do I do this? Well, let's say my first number in the set is a 1. Can't choose a 2, can't choose a 3, but I can choose a 4. Once I choose the 4, I can't choose a 5 or a 6, but then I can choose any of these numbers right here, 7 through 12. So that gives me 6 possible ways of doing that. Now I start with 1 as my first number. I'll choose 5 this time. And now for my third digit, I cannot choose 6 or 7, but I can choose any of these guys. So there's 5 of those. But I can also, instead of a 1, I can put a 2. That's allowed because those are not consecutive. So for this also gives me another 5 possibilities. So that gives me 10 in total. Okay? Now let's look at the next one, which is 6 for the middle number. Now, if 6 is my middle number, I cannot choose 4 or 5 or 7 or 8. But for the first number, I can choose any of those 3. So I've got 3 possible choices there. And then for my third number, I can choose any of those 4. So I've got 4 possible choices there. So 3 times 4 is 12. All right, does that make sense? I hope. Now let's keep going. Middle number is 7 this time. If my middle number is 7, I am not allowed to choose 5 or 6 or 8 or 9. But for my first number, I can choose any of these guys. So I've got 4 possibilities there. And for my third number, I can choose any of these guys. So I've got 3 possibilities there. So again, 4 times 3 is equal to 12. Okay. And then if my middle number is 8, again, in a very similar way, we can look at the number of possibilities. My middle number is 8, can't choose 6 or 7, 9 or 10, but for my first number, I can choose any of those 5. And for my last number, I can choose any of those 2. So 5 times 2 gives me 10. And finally, if my middle number is 9, I've got to figure out how many possibilities. If my middle number is 9, I can't choose 10 or 11 or 7 or 8. But for my first number, I've got 6 possible choices. And for my last number, I can only choose a 12, and that's 1 choice. So that's 6 times 1, which is 6. So I've got to add all these guys. 6 plus 10 times 2, 32. 32 and 24 is 56. And that, if I use this choose notation for k equals 3, would be 8 choose 3, which is indeed equal to 56. All right, so by this point, I hope you're convinced that the choose notation works, and therefore for k equals 4, it would be 6 choose 4, and that is equal to 15. And that's it. You cannot make a size set of 5. It's impossible. And if you try, you'll see that it won't work. So all I have to do is now add up my total number of sets to get the final answer. And if you do that, you get a total sum of 129. And therefore, number 25, the answer is E. A sequence A1, B1, A2, B2, A3, B3, ... of points in the coordinate plane satisfies AN1, BN1 is equal to root 3 AN minus BN, root 3 BN plus AN. For n equals 1, 2, 3, ... Suppose that A100, B100 is 2, 4. What is A1 plus B1? We have to start somewhere in this question, so obviously we will start with just A1, B1 and work our way forward. And just for simplicity, I will let A1, B1 just be X and Y like that. So entirely using this formula, let's proceed with A2 and B2. And I'll leave the algebra up to you. I'll just give you the summary. If you do the algebra involving this, you get the following result: root 3x minus y, root 3y plus x. Continuing, A3, B3, you will get 2x minus 2 root 3y and 2y plus 2 root 3x. Continuing for A4, B4, you will get the following result: minus 8y and 8x. And this is a pattern that continues, and you can conclude at this point that an plus 3 and bn plus 3 will be negative 2 to the power of 3 bn, 2 to the power of 3 an. Just like how we got this right here. This pattern will repeat itself if you continue to do the algebra. So let's continue in this same pattern. And you get A7, B7. Let's just concentrate on every third one since we have a formula for every third one. A7, B7 will give you minus 2 to the power of 6x minus 2 to the power of 6y. A to the 10, b to the 10 will give you 2 to the power of 9y and minus 2 to the power of 9x. A to the 13, b to the 13 will give you 2 to the power of 12x and 2 to the power of 12y. And if you keep going in that pattern, you will be able to conclude that A100, B100 is equal to minus 299y and 2 to the 99x. Okay, so at this point, we know from the question that A100, B100 is 2 and 4. They've given that in the question. So now we can solve for y and x. So solving for y, we get that 2 is equal to minus 2 to the power of 99y, and therefore y is equal to 2 over minus 2 to the power of 99. And solving for x, you get x is equal to 4 over 2 to the power of 99, like that. And recall our x and y were representing a1 and b1. So if we want to figure out a1 plus b1, then that is just going to be x plus y. X is 4 over 2 to the power of 99, and then we are going to be adding negative 2 over 2 to the power of 99. So that becomes 2 over 2 to the power of 99, and simplifying, it's 1 over 2 to the power of 98. 1 over 2 to the power of 98 is answer choice D for number 25. The first two terms of a sequence are a1 equals 1 and a2 equals 1 over root 3 for n greater than or equal to 1. an plus 2 is equal to an plus 1 over 1 minus an times an plus 1. What is the absolute value of a to the 2009? Well, I hope you can recall a certain trigonometry relationship, and that is the tan of a plus b. Why is that important? Because it looks very similar to this right here. Tan of a plus b is the tan of a plus the tan of b all over 1 minus the tan of a times the tan of b. And as you can see, it's very similar. So that means that instead of a plus b, if I were to put the tan, say, of theta n plus 2, it behaves identically. So it would be the tan of theta n plus the tan of theta n plus 1 all over 1 minus the tan of theta n times the tan of theta n plus 1, right? So that means that the tan of theta n plus 2 is equivalent to this combines into just the tan of theta n plus theta n plus 1. So as you can see, you can get a very quick relationship using the tan formula. And this further, if you drop the tans, just means that theta n plus 2 is equal to theta n plus theta n plus 1. So this allows us to figure out what is going to be the pattern here. Now, we were given these values, right? But we changed them to tans. So A1, they tell us is 1, but that is equivalent to the tan of 45. So our theta 1 is 45. And then they also tell us that A2 is equivalent to 1 over root 3, and that is the equivalent of the tan of 30. So our theta 2 is equal to 30 degrees. So we can now extrapolate this and use this formula very quickly to figure out the pattern. So let's see here. So theta 1 is 45, theta 2 is 30. To get theta 3, I just use this formula. I just add the previous 2 and I get 75. To get theta 4, I add the previous 2 and I get 105. Get theta 5, I add the previous 2 and I get 180. But the tan of 180 is equivalent to the tan of 0. So I can use 0 since this is also equivalent. It's just quicker to do it with this formula. So I revert to 0 now. Now add the previous 2, I get 105. Add the previous 2, and you just keep going like this, and I'll just fill in the values. Here we get 300, but 300 is equivalent to 120 if you were to take the tan of it. And similarly, you make similar substitutions to get 105 and so on. And when you go through this big long process, you'll see that finally, after 24 terms, there is a repeating pattern. It goes back to 45, 30, 75, 105, like that. So this pattern repeats every 24 terms. So we were asked to figure out the 2009th term, like that. So, well, first thing we need to do is figure out, is 2009 divisible by 24? And the answer is no. It's 83 with a remainder of 17. So that means that 2009 will be equivalent to the 17th term in this pattern, which is this guy, 0. So that means that a to the 2009 is equivalent to 0. And therefore, number 25, the answer is A. Two quadrilaterals are considered the same if one can be obtained from the other by a rotation and a translation. How many different convex cyclic quadrilaterals are there with integer sides and perimeter equal to 32? We have some quadrilateral and they're telling me that it's cyclic, and that's great. So we have A, B, C, D, like that. And they have told me that the perimeter, which is obviously A plus B plus C plus D, has to be equal to 32. And not much else is given in terms of information. Well, immediately by the triangle inequality, I can tell you that B plus C plus D obviously has to be greater than A. Now B plus C plus D is 32 minus A from this equation. And therefore 32 is got to be greater than 2A, and therefore A has to be less than 16. So A can be 15, 14, all the way down till 1. So that's the first piece of information. Now, to figure this question out, we have to look at 4 different cases. Actually, 5 different cases. And they get progressively more difficult, so just be prepared. Case number 1 is when all the sides are equal. And since the perimeter is 32, each side must be equal to 8. And how many ways are there to do that? The number of quads, short for quadrilateral, well, there's only one, right? One quadrilateral that has the sides 8, 8, 8, 8. Okay, we're done with case 1. Case 2. Case 2 is when 3 sides are equal. Now, if 3 sides are equal, there's only a few ways of doing that. We can have A, B, C, and D as follows. We can have 10, 10, 10. And if we do that, becomes 2 for A, which is allowed. We can have 9, 9, 9, and that means A would be 5. We can have 8, 8, 8, but if we do that, it becomes the same as that, so that's a double count. 7, 7, 7, and 11, and then 6, 6, 6, and 14. We can't go any more because then A would become greater than 15, and remember, A has to be less than 16. So this one gives me 4. Okay, these are the easy ones. Now we get into case 3, 4, and 5, and that's going to be hopefully not too bad, but it's very time consuming, and I always wonder, how do people do this on a math contest, which gives you about 3 minutes? Case number 3 is when you have 2 pairs of equal sides. So one such example is that, A equals B and C equals D, right? So for A and B, you can have any number from 9 to 15. And the corresponding number for C and D would be any number from 1 to 7. So for example, if A was equal to B is equal to 7, then the corresponding numbers for C and D would be 9. It would be 14 plus 18, which is equal to 32. Now, for each of these, the quadrilateral can be arranged in 2 different ways. The first way is when you have the 9 as opposites, like that. The other way is when you have the 9 and 9 side by side. See that? One looks like a kite, the other one is obviously a rectangle. So for each of these, you would have 2 different quadrilaterals. So 9 to 15 gives you 7 possibilities, but for each of those, you get 2. So 7 times 2 is the total number, and that is 14. So that takes care of case number 3. Just remember, for each of these forms, you can create 2 different quadrilaterals, a rectangle and a kite, like I drew. Now we are into case number 4. Case number 4 is when you have 2 sides that are equal. Now, if 2 sides are equal, we have quite a few scenarios. I'll give you just the first couple. For example, if you have sides that are equivalent to 2, so you have A is equal to B is equal to 2. Then the other two, C must be equal to 13, and D must be equal to 15. And another example I'll give you is if A and B are equal to 3, then we've got a few more scenarios. We've got C could equal 12, D could equal 14, or C could equal 11, and D could equal 15, like that. So for the first one, for example, you get only 1, this guy. And then for this one, you get 2 possible sets. And very similarly, when you keep on going like that for A plus B, A equals B equals 4 and all that, it becomes pretty complicated. It gets up to like this: 3 sets, and then 4 sets, and then 4, and then 5, and then 7, and then 5, and then it comes back down to 4, 4, and then 3, 2, and 1. Each of these corresponding to a different integer that you've selected for A and B. And when you add all these up, you get 45. But what makes this even more complicated is that for each of these sets, there's 3 different scenarios. So I'll explain that. Let's say you've got one quadrilateral, another quadrilateral, and another one, right? So for example, let's say you have this first one, 2, 2, 13, 15. It can be drawn like this: 2, 2, 13, 15. It could be drawn like this: 2 here, 2 here, 13, 15. Or it can be drawn like this: 2 here, and the 15 here, and the 13 there. So since each of these produces 3, we have to multiply that 45 times 3. And if we do, we get 135. And that is how many there are in case number 4. And now finally we have case number 5. And case number 5 is when no sides are equal. So, for example, A can be anything from 15 down to, in this case, 9. Because once it gets into the 8 and all that, then we can't have no sides equal. And for each of these, we have to now count cases. So for example, when A is 15, that means B plus C plus D are 32 minus 15, which is 17. And then we have to figure out what are the possibilities for B, C, and D. And if you do all that, and I'm going to save the headache for you guys, you get 69 possible side lengths, 69 possible scenarios. And for each of those, 6 different quadrilaterals can be formed. So for case number 5, we have to take that 69 and multiply it by 6. And that gives you 414. So the grand total is going to be this 1, this 4, 14, 135, and 414. And if you add up all those, you get a grand total of 568. And therefore, the answer for number 25 is C. Triangle ABC has BAC equal to 60 degrees. Angle CBA is less than or equal to 90. BC is 1. AC is greater than AB. Let H, I, and O be the orthocenter, incenter, and circumcenter of ABC, respectively. Assume that the area of the pentagon PCOIH is the maximum possible. What is the angle CBA? First, let us describe what all of these things mean. So if I have a triangle and I want to figure out its orthocenter, what I do is I draw perpendiculars. So I draw a perpendicular to there, and I draw a perpendicular to here, and I draw a perpendicular to here. And that point where they meet is the orthocenter. Basically, it's the intersection of the altitudes. And they are saying it's H in their diagram, in this question. Now let's draw another triangle to explain the incenter. The incenter is a little bit different. It involves angle bisectors. So you're going to bisect this angle like that as best as I can. Bisect that angle, cut it in half the best that I can, and then bisect that angle the best that I can. And the point that those angle bisectors meet, that is the incenter. And they're calling that I. So for example, if this is X, this will be X, that angle. If this is Y, this is Y. And if this is Z, that's Z. Those angles were bisected. Now let's talk about the final one, which is the circumcenter. That is a little bit different. That involves basically drawing perpendiculars that will cut the sides in half. So for example, the first one approximately here. So what happened here is you drew lines that were perpendicular, but when you drew them, they cut each side into half. So that side is cut into half like that. I hope that makes sense. So it's the intersection of the perpendicular side bisectors. And in this question, they're calling that O, that point right there. So that is the orthocenter, intercenter, and circumcenter. And now let's begin the question. Here's a diagram that describes all of this, and we're probably going to have to look at this diagram throughout the question, so I'll probably have to write it a few times because it will get quite crowded very quickly. First, by the inscribed angle theorem, this angle right here is twice this angle. So that basically means that BOC is twice of BAC. But the question has told you the actual value of BAC, it's 60 degrees. So very quickly we can figure out that BOC is 120. Now by the opposite angles, we know that BHC, which is BHC, is the same as EHD. Now, I think it's helpful to label the fact that these are 90 degrees. And the reason is because H has been drawn in a way that it reflects the orthocenter. And if you remember, the orthocenter is when the lines meet at a right angle. They're basically altitudes. So that means E is 90 degrees. And since D is also a line that goes through H, that is also 90 degrees. Okay? And we know that the question actually told us that this is 60. From there to there, 60 degrees. So, since BAC is 60 and that's 90 and that's 90, we can easily figure out this because that's basically a quadrilateral. This whole thing is a quadrilateral. And the sum of the angles of a quadrilateral are always going to be equal to 360. So that means that EHD is basically 360 minus 60 minus 90 minus 90. So EHD, that angle, is 120. And since BHC is equivalent to that, BHC is also 120. Now notice that BI and CI, so we got BI right here and CI, those obviously meet at I. And what was I? It was the incenter. An incenter involved basically the intersection of angle bisectors. So because those are angle bisectors, BI and CI will cut those angles in half. And if you look at the triangle BIC, that angle will be equal to 180 minus ICB minus CBI, since the sum of the angles in a triangle add up to 180. So that means we have 180, but ICB is basically, since IC is an angle bisector, it is essentially just ACB divided by 2. This whole thing divided by 2, since IC is an angle bisector. So I can write that ACB divided by 2. And very similarly, CBI, since BI is an angle bisector, CBI is really just CBA divided by 2. So this is CBA divided by 2. So we've got now 180 minus ACB plus CBA over 2, if you put that in brackets. But ACB and CBA are very easy to figure out because ACB, that angle, plus CBA, those two plus 60 all add up to 180. So those two must add up to 120. So that means this is 180 minus 120 divided by 2. And therefore we get an actual numerical value, and that's 120. And that is for BIC. So something you'll notice here, BOC was equal to 120. BHC equal to 120. BIC equal to 120. So let's draw those. BOC, that's 120. BIC, 120. And then BHC is also 120. So that means that H, I, and O must fall on a circle. And that's why this diagram is written and drawn like this. So all of these points B, H, I, O, C are on a circle. And that will help us solve this question. So let's keep our diagram in the screen. Now we've got to look at a few more angles. The next angle we're going to look at is OCI. And OCI is right here. OCI. It's a small angle right there. And that angle, of course, is equal to ACI minus ACO. So it's ACI minus ACO. If you do that, you'll get this one. And that ACI is equal to ACB over 2, because remember, that was an angle bisector. And ACO, you can figure out pretty quickly if you understand the fact that O represents a line that actually bisects AC, right? If you go back to the definition of O is the circumcenter. And the circumcenter is basically the intersection of the perpendicular side bisectors. So what's happening is you're drawing a line from O to AC such that it basically bisects AC. And that line not only bisects it, it's perpendicular. So the first thing that means is that this angle will be the same as that angle. And then you can just, to find ACO, all you have to do is just subtract from 180 this 90 and this angle right here. So what you're basically doing is doing 90 minus half of COA. So I hope that makes sense. And then very quickly from this, because of the inscribed angle theorem, you can deduce that COA, half of it, is the same as CBA, right? Because this is going to be double of CBA. So half of COA is the same as CBA. So this just becomes CBA. And the rest is all the same. 90 minus, and this is ACB over 2. Now at this point, ACB over 2, we can just leave it as is, and then we can bring out the 90. But now we have this plus CBA. And at this point, CBA is pretty easy to figure out, because CBA is just that big angle. Since this is 60, that is basically telling us that CBA is the same as 120 minus ACB, since the sum of the angles are equal to 180 of a triangle. So now we have pretty much boiled it down to just ACB over 2 minus ACB, so that's minus ACB over 2, and that is, of course, 30, not minus 90 plus 120. So that takes care of OCI. Now we want to take our attention to ICH. ICH, this angle right there. And that is equal to ACH minus ACI, right? Because you have ACH and then you subtract from it ACI in order to get ICH. And if you do that, you will notice ACH is 30. Why is it 30? Well, look at this triangle, this one right here, right? This is 90, this is 60. So that means this has got to be 30, and that is ACH. So that's why it's 30. And then ACI, well, that's just equal to ACB over 2, right? Remember, CI was an angle bisector. So if it's cutting it in half, it's basically cutting ACB in half. So it's ACB over 2. So notice for OCI we got 30 minus ACB over 2. For ICH we got 30 minus ACB over 2. So that means since those two angles are equal, OI must be the same as IH. OI must be the same as a line from I to H. Not the arc, but the line, because those two angles are the same. And those two angles are OCI and ICH. So now we're in the final stage of our question, and let's go back and refresh our memory. What do they want us to figure out? They want us to figure out the angle CBA. But when we have a very specific condition, and that is when the shape of BHIOC is maximized. Now, BHIOC is right here. BHIOC. That is that shape. It can be broken up into two shapes. First, the BCO, which is just this triangle, and then the leftover shape, which is BHIO, like that. Now recall what O is, right? O is the circumcenter, so it has perpendicular side bisectors. So it has a line going down that cuts BC in half, and that line is perpendicular. So what that basically means is that this triangle BCO is an isosceles triangle. And since the question tells us that BC is equal to 1, we can easily figure out its area. This angle is 60, and we had earlier figured out that BOC from the inscribed angle theorem is 120. So since this angle cuts that in half, BC in half, this must be 60 degrees, and this must be 60 degrees, like that. And therefore, this in here is 30 degrees. And we can easily see that that is an isosceles triangle, and its area will be fixed. If you're interested, we can easily figure out the area of BCO. It will basically be 1/2 base times height. The base is 1. And the height, of course, is this distance from top to bottom. And that distance you can figure out with the 30, 60, 90 triangle, that height is going to be 1/2√3. So that's a fixed number. So really the only thing we need to look at is this BHIO. If we want to maximize this, we have to maximize that. So let's concentrate on maximizing this. That is maximized when you have the following scenario. OI must be equal to IH must be equal to HB. So this distance, OI, must be the same as IH, must be the same distance as HB. If that is set in place, you'll be able to maximize the area of BHIO. So that means our angles become as follows. OCI would therefore be the same as ICH. And it is here, as you can see. And another angle that we have to equate is HCB. That also will have to be the same. So OCI will have to be the same as ICH, will have to be the same as HCB. And all of those, if you add them up, equal OCB. So if they're all equal, all of them have to be 1/3 of OCB. And OCB from this diagram, I just labeled it, it's 30 degrees. So it's equal to 10, each of those angles. So finally, we have to now figure out CBA, right? And we can do that. First, let's use this formula. OCI is equal to 30 minus ACB over 2. OCI we just figured out as 10. So that's 30 minus ACB over 2. So that means ACB over 2 is equal to 30 minus 10, which is 20. So therefore ACB is equal to 40. And our very last step of the question is trying to figure out CBA. Well, CBA should be very easy to figure out. It's 180 minus this 60 minus ACB, and ACB we just figured out was 40. So that means CBA is 80 degrees. 80 degrees is the answer to this question, and therefore that would mean it is choice D. Let f of x be the absolute value of 2x bracket minus 1, where x bracket denotes the fractional part of x. The number n is the smallest positive integer such that the equation n times f at x is equal to x has at least 2012 real solutions x. What is n? Note, the fractional part of x is a real number, y is equal to x bracket, such that y is greater than or equal to 0, less than 1, and xy and sy is an integer. Well, this question requires some graphs. And this is the first one. This is the graph of f at x. And that is the absolute value of 2 times x in a bracket, like that, minus 1, where x is the fractional part, x bracket is the fractional part of x. So as you can see, you got 1 up here, and you've got 1 down here, and so on, right? So it's a zigzag pattern. Now what we have to do is draw 2 more graphs. And the next graph we have to draw is the graph of f at x times x, that one. And that one, I will walk you through that one. Let's draw this pattern here, and off we go. So again, I'm going to draw this a little bit bigger in terms of like the values, because I've got to squeeze it all in. So let's see here. It won't be perfectly drawn to scale, but hopefully you'll get the idea. So if you were to just look at this graph right here, and then all you're doing is multiplying by x every time, then you get the following pattern. And let me just label this in now. 1, 2, 3, and this is 1, 2, and 3. And that's the zigzag pattern you get this time. As you can see, it's a little bit different, but it still is a up and down type of scenario. Now you think, okay, well that doesn't seem so bad, but unfortunately we have to now draw this one. Remember, f at x now has to be put inside that. So it's going to be this monster right here. And if we go back to the original definition, this is actually the absolute value of this time the bracket has x times f at x inside, and then minus 1 absolute value. So now we got to draw this. So this one is a little bit trickier, but there's some good news here that it never gets bigger than 1. So that's why the axis here on y is only 1. So in the initial part of the graph, it's behaving in a way that's kind of strange up there. But then eventually it drops down to the 0 and then goes right back up to 1. So that's the first part. And then from 1 to 2, it starts developing a pattern that is very helpful to us. It drops down like this and goes back up to 1. But then in the second half, from here to here, it actually drops down twice. So it'll come down once, come back up, and then come back down again, and then come back up. And then from 2 to 2.5, it will again come back down and go back up twice. So once, and then twice, and then once, and then twice. But then from 2.5 to 3, it'll come back down and up 3 times. So once, twice, once, that twice, and then a third time here. So like that. And then that's the pattern. Now, this has to equal, if you remember, x over n. So x over n is obviously some straight line, and it has to equal. So it's going to go through somewhere like that. We're not entirely sure, but something like that. And the intersection points are basically the solutions to this equation. So we have to start counting intersection points, okay? From 0 to 1, it looks like 1, 2 intersection points. So let's put that there. 2 intersection points. And then from 1 to 2, we have 1, 2, 3, 4, 5, 6 intersection points. So I'll put 6 there. And then from 2 to 3, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intersection points. So I'll put that there, 10. So as you can see, each time it's going up by 4, like that. So if I were to do from 3 to 4, it would be 14 intersection points, and so on. So that means this behaves as follows. The intersection points will be 2 plus 6 plus 10 plus 14 and so on, right? Dot, dot, dot. Now, if you were to factor out a 2, you will see this is 1 plus 3 plus 5 plus 7 plus dot, dot, dot. And that's obviously the sum of the first n. If it goes all the way up until n, it's the first n odd numbers, and the sum of the first n odd numbers is always equal to just n squared. So this is just 2n squared. And our question says that we want more than 2012 solutions. So that means this 2n squared has to be greater than or equal to 2012. So that means n squared has got to be greater than or equal to 1006. And the first time that you get an integer solution for this is when n is equal to 32. So the answer to this question is 32, which is choice C. Let f, c going to c, be defined as f at z is z squared plus iz plus 1. How many complex numbers z are there such that the im of z is greater than 0, and both the real and the imaginary parts of f at z are integers with absolute value at most 10? Well, we have an expression that f at z is equal to z squared plus iz plus 1. Now, immediately I can just put the real part here and the imaginary part separate, like that. And then if I were to put in any real number, say r, into this, it would be of the form r0, because the imaginary part I'm putting as 0. And if you do that, f at r would basically be r squared plus 1 plus ir. And that basically means that this was translated to r squared plus 1 r, like that. This is the real part, and this is the imaginary part. and the imaginary part is r. And that's what this represents. That's the translation that's been made. So we can make a graph to sort of illustrate what's happening. And it won't be the greatest graph in the world, but it's just to illustrate. And this graph is going to be a little confusing because you've got two scenarios. You have the first scenario, which is x and y, which is the scenario that everybody's used to. But then you also have imaginary and real. So instead of one graph, I'll draw two graphs. And then we have to combine them. So here's the first graph, and here's the second graph. So the first graph is, your standard one, x, y. And then the second graph is, of course, real and imaginary. So you have the I up there. Okay, now this is the one that I really would like to talk about, the one with x and y. And in particular, this transformation, whatever you want to call it. It basically creates a parabola like this. And that parabola is going from r to r plus 1. So it really is represented by the equation x is equal to y squared plus 1. Okay, so that is going to come in very handy later on. Now we get into the real and imaginary part of it. So now I have to start talking about this. Now, what I'm going to do is complete the square here because I'm interested in sort of my max or min whatever, and the only way I can figure that out is if I complete the square. So let's do that, and that's going to be z squared. Remember, you take half and square it, so I'm going to take half of this, and half of I is I over 2, so I over 2 squared. And then, of course, I have to immediately subtract it. Anything I do to the equation, I can't just keep. I have to subtract. And then a plus 1. And as you know, the good news is that this allows me to factor these guys. And if I do, it becomes z plus I over 2 all squared. And then this becomes negative I squared. Well, I squared is negative 1, so that's negative 1. So 1 over 4 plus 1, which is 5 over 4. So what this tells me basically is that anytime I put in a value of anything that has negative I over 2, so for example, if I put r minus I over 2, like that, when you plug that into here, the negative I over 2 cancels with this I over 2, and it would just give you a real result. So this, for example, would just be r squared plus 5 over 4, because as you can see, the I over 2 canceled. So that's very helpful because it allows us to kind of continue with these graphs. So essentially, in very simple terms, what that means is that I can get all real values as long as I start with something that has negative I over 2 as my complex number. So that means I can get all my values on here, even if I'm starting with complex numbers, as long as the complex number has negative I over 2. So now I get to the part that's talking about this absolute value at most 10. What do they mean by that? What they are referring to there is that if you take any point and you look at the real and imaginary parts, right, their absolute value has to be at most 10. So that is the equivalent, really, of a grid on the number line that is 10 by 10. So if I were to draw, let's say, a 10 by 10 square, so something like that, as long as the points are within that 10 by 10 square, it would satisfy the second sentence of that question. So this is, of course, way out there, 10, 10, and this is 0. And then this is, of course, minus 10, 10, and so on. Negative 10, minus 10, and this is 10, negative 10. So what we're really referring to is lattice points. We want lattice points which represent points that have integer values, right? So how many are there in total before we get into the discussion of, what we have to calculate? Well, on the number line from minus 10 to 10, there's 21, right? 1 through 10, negative 1 through negative 10, and then the 0. Don't forget the 0. So there's 21 integers that way, 21 integers that way. So the total number of lattice points would be 21 times 21, which is 441. So that's our total. And we have to now figure out how many are going to be in our special region. In our special region, remember we had that parabola. And we have to figure out lattice points that are in our region. In our region are basically the ones that are on or to the right of the parabola. So I'll write that in here. So let's figure this out. Let's make a little table and try to figure out how many of these we will get. So we got x and y, and our equation, if you recall, was x is equal to y squared plus 1. Okay, so when x is, say, or let's look at y first. When y is 0, if y is 0, then that means we are here. We're basically here on that x-axis. If y is 0, we want all the lattice points from here to here. Now, this is not drawn to scale, but this point right here is represented by a 1. So any lattice point from 1 to 10 will be included, and that's 1, 2, 3, 4, all the way up until 10. So 1, 2, 3, all the way up until 10. Those are going to be valid lattice points if you combine them with y equals 0. So I've got 10 of those. Now let's start talking about different values of y. How about 1? When y is 1, now that means we are approximately here on the y-axis. So we're here. When that happens, x is going to be equal to 2 if you sub y equal 1 into there. So that becomes 2. So x is approximately, like I said, not perfectly drawn to scale, but it's approximately here, right? Where that's 2. So that's 2, let's say. But x now can be any value from 2 to 10. 2 can be included, but we can also put in all the values up until 10 to satisfy this condition. So 2, 3, all the way up until 10. And that is 9 values. Now let's calculate what happens when y is 2. When y is 2, this equation becomes x is equal to 5. So now we're up to about 5 when x is 2. So approximately, well, is very, very much not drawn to scale, but so when y is 2, x is 5, so we got 5 here. So now the only points we can get are in that range. So it could be 5, 6, all the way until 10, and that's going to give you 6 values. 6 possible lattice points, 2 combined with any of these. And then let's keep going here. How about when y is 3? When y is 3, we get x equals 10, so that's right at the boundary. When y is 3, you're going to have x equals 10. So the only one that works there is 10 for a value of x, and that's obviously just one such point, 3, 10. And then what's interesting is that if you go the other way, minus 1, minus 2, minus 3, you get the same scenarios. And that would mean 9, 6, and 1. So you add all these up to get the total number of lattice points, and when you do, that is 42. But what the question was asking is for us to figure out all the lattice points in this range, right? I did it for this range because it's easier to count. As you can clearly see, 42 is definitely a lot less than 441. So what they wanted is all the lattice points in that range. Well, how do you get that? Well, that's pretty straightforward. You just take the total number of lattice points, which is 441, and subtract from them the lattice points in that region that I concentrated on. and that's 42. And when you subtract those, you get 399, and that represents the number of lattice points in that region, which is the region they are interested in the question stem. So, doing all this, the answer is 399, and that would be choice A. The parabola P has a focus 0, 0 and goes through the points 4, 3 and -4, -3. For how many points x, y that are part of the element of P with integer coordinates, is it true that the absolute value of 4x plus 3y is less than or equal to 1,000? First thing I'd like to do is draw this diagram and let's discuss it a little bit. So it's not going to be beautifully drawn to scale, but I'll try my best. So here we go. And then let's just use the information they give us. 4, 3 and 3, 4, so approximately here. And -4, 3, so here, approximately. And that is the 2 points. So let's just draw a line connecting them like that. Now very quickly, because this is 4 and this is 3, I know that this is going to be 5, right? Because that's a 3, 4, 5 triangle. And the same story here. This is 4 and this is 3, so that's going to be also 5. So that hopefully will help us. They made it a little bit easier for us with that 3, 4, 5 right triangle. Okay, now what I have to do is I have to draw this parabola. The focus is right here, 0, 0. So this is 0, 0. Obviously, that's the origin. I'll just put a little F for focus right there. And we've got to draw a directrix. Now, the directrix depends on how the parabola opens. Does it open like this or does it open like that, right? And that's something I honestly don't know, but I'm going to do the solution the correct way. And that is basically a parabola that opens like this. So something like that, in a very sort of very sketchy way. Okay, so now what we have to do is we have to draw the directrix. So how do we do that? The directrix is basically a line. It's going to be something like this. And where it exists is basically that the distance from any point on the parabola, so let's say this point to the focus, is the same distance as the point to the directrix. So the directrix has got to be somewhere along there. So let's just draw an approximate place for that directrix. So approximately there. And just to recap, the distance from this point to the directrix has to be the same as the distance from that point to the focus. So the distance from that point to the focus is 5, so this distance has to be 5 also. Okay, and this line is the directrix, like that. And then the good news is we can approximate these points, that point, and of course the point on the other side, which is right here. We can approximate that because it's 5 in distance. So if I were to draw sort of a sketch, if I'm going 3 this way, 4 up, I'll be able to figure out that point. And 3 going left and 4 up from this point right here would basically be 1, 7. So this point is 1, 7. And in a very similar way, we can sort of say, since this is 5, 3, 4, 5 triangle would basically be going up 4 and going across 3 from this point. So if you go up 4 from that point and across 3, it would be -7, 1, this point right here. So there we go. We got 2 points, and then we can find the equation of the directrix line. And the directrix line, I'll let you do that. I mean, there's 2 points, and as you know, all you have to do is sub in those 2 points into y equals mx plus b. and you'll get the equation. And when you do, you get the equation y is equal to 3/4 x plus 25 over 4. That's the equation of this line right here. That's the directrix. Multiply through by 4, and you'll get 4y is equal to 3x plus 25. All right. Now at this point, we have to talk a little bit about something very important, and that is the point line distance formula. The shortest distance from a point to a line is the perpendicular distance. So if you have a line that has this equation and you want to figure out the distance from a point to that line, which is represented by d for distance, it's this formula right here. So I have to apply that to this equation right here. And then in particular, let me draw in the diagram what it is I'm referring to. I'll just draw one such point. So let's just say right here. So something like that, that red line, or any shortest distance from the point to a line. So for example, from here to here, let's say, if the point is here, from here to here. And of course, these are all going to be right angles like that. Okay, well, applying this formula, it would basically be d is equal to, and remember, this is my line this time. So let's put this all in one side because we have to get it in this format. So it would be 3x minus 4y plus 25 is 0. Okay, so using this formula now, d is equal to 3x minus 4y plus 25, the absolute value, over the square root of a squared, which is 3 squared right here, and b squared, which would be -4 squared, like that. Okay, so no trick so far, just that formula. Now, here's the part that is a little bit tricky. Let's say this point right here is xy, right? That point right there. Well, just like how they put xy right here. I'm interested in this whole parabola. I want something that's true for the entire parabola, and any point xy like that. Now, this is not perfectly drawn to scale, so it might be a little bit harder to understand, but let's just recap that any point on the parabola, if you draw a line from it to the directrix, like I have drawn right there, and then you draw a line from the same point to the focus, like that, those distances have to be the same. So it's probably best illustrated in the one that is labeled 5, right? This point right here is best illustrated in terms of the way the diagram looks. So that point, for example, is 4, 3. If you drew a line from that point to the directrix, the distance is 5. If you draw a line from that same point to the focus, the distance is 5. And that's true for any point on the parabola if it was perfectly drawn to scale. Now this point is represented by 4, 3, but in general it's xy, right? So if the distance from xy to the directrix is 5, I can also call that d, just like I call this d right here. And the distance from here to here must also be d. In this case, it's 5. Now, here's the thing. Look at this d right here. That d and this xy have a relationship. This is x, this is y. What's that relationship? A Pythagorean relationship. X squared plus y squared is equal to d squared. And that is a very important aspect to this question because it allows you to substitute x squared plus y squared over here. But remember, we're substituting for d squared. This is not d squared, this is just d. So we have to square this whole thing in order to make it d squared. So it would basically be 3x minus 4y plus 25, absolute value, all squared. And then the bottom, when you square it, the radical sign just disappears. So it just becomes 3 squared plus 4 squared. All right? And this is the equation that's going to help us solve the question. All right, we've gone down to a very, very good point in this final question. Now, we have to rearrange this, and you do some algebra and to rearrange it. And then when you do, you get the following. You get 4x plus 3y all squared is equal to 25 times 6x minus 8y plus 25. Now, at this point, we have to backtrack and look at what the question is asking. It is asking that if you have 4x plus 3y less than 1,000, for how many points can you get integer coordinates so that this is true? All right, well, let's see. In order to make this a little more digestible, this part here I'm just going to call m for now. So this boils down to just m absolute value is less than 1,000. And since we've got a bunch of 25s in here, I am going to write m is equal to 25k, and that will help me simplify things a little bit better. And then substitute that into this guy right here. So when you do, you get m right here, but that is 25k. So it'll be 25k all squared, and this is 25 times 6x minus 8y plus 25. Now the 25 squared will cancel 125 with that guy, so we will just get 25k squared is 6x minus 8y plus 25. And this will be my equation 1. My equation 2 will just be this one right here. Right here, where in particular 4x plus 3y is equal to 25k. That is my equation 2. 4x plus 3y is 25k. And now we have to solve these two. So solving, we get x is equal to 1/2 3k squared minus 3, and y is equal to minus 2k squared plus 3k minus 2. And the values of k that make x, y have integer coordinates, if you look at these two, you will see that those are odd integers. And therefore, for this range, which was 25k less than 1,000, if you look at what we did up here, those values of k are k equals minus 39, minus 37, minus 35, ... 35, positive 37, 39. And when you add up these guys, those give 40 values. So 40 is the answer to this question, and therefore number 25, that is choice B. A collection of circles in the upper half plane, all tangent to the x-axis, is constructed in layers as follows. Layer L0 consists of two circles of radii 70 squared and 73 squared that are externally tangent. For k greater than or equal to 1, the circles in the union from j equals 0 to k minus 1, Lj, are ordered according to their points of tangency with the x-axis. For every pair of consecutive circles in this order, a new circle is constructed externally tangent to each of the two circles in the pair. Layer Lk consists of the two k minus 1 circles constructed in this way. Let S be the union from j equals 0 to 6 of Lj, and for every circle C, denote by RC its radius. What is the sum of 1 over the square root of RC, where C is element of S? Well, what are they talking about in this question? They want you to figure out all the radii and then add their reciprocals. So essentially add the reciprocals of the square roots of all the radii of the circles, and that's what basically that means. Okay, so what we want to do is first draw a diagram, and hopefully that diagram will make some sense. Okay, so let's carefully just use the two biggest circles and the third circle that's in between them. Now what I did was I wrote the radii basically of these three circles, and let's label these now. I'll call this C, I'll call this A, and this is of course C, C, this I'll call B, and this is B, this is A, this is A, and this is B. Okay, so now let's try to figure out some sort of a relationship. One line that's going to help me is a straight line across, and another straight line across up at the top. So now let's carefully label this here. This part here, all the way from top to bottom, is B, right? And this part from here to here is C. So this is C also, from here to here. So that means from here to here, that distance is B minus C. All right. And therefore, we can now figure this out. And from here to here, I will call that X. I don't know what it is. Okay, so let's use this triangle Pythagorean relationship. So we've got X squared plus B minus C squared is equal to B plus C squared, which is the hypotenuse of that triangle. So this leads to X squared plus B squared minus 2BC plus C squared is equal to B squared plus 2BC plus C squared. So a lot cancels, and in the end we're left with just 4BC is equal to X squared. So that means X is equal to 2 root BC. So I can put that in here, 2 root BC. And then on this side, if we do the exact same thing, let's say that is Y, and I'll let you do the algebra. It's identical. It will come to the same sort of relationship, that it will be 2 root of AC, because those are the variables on that side. Okay? And then this triangle up top here, I'll do that one. It's pretty much identical, but I'll just do it. I'll call that whole distance from there to there, let's say call it L for length, I guess. So that means L squared plus this distance, which is the equivalent of B minus A squared, is equal to the hypotenuse, which is B plus A. And when you expand this all out, you will get that L squared is equal to 4AB, and therefore L is equal to 2 root AB. 2 root AB. There we go. Okay, so now at this point, you will notice something, that from here to here is this plus this, and from here to here, which is the exact same, is that. So we can set them equal to each other. That's very helpful. So when we do, we get the following. We get that 2 root AB is equal to 2 root AC plus 2 root BC. Divide through by 2's, and that just gives me root AB is root AC plus root BC. Now divide everything by the root of ABC. And when you do that, something great happens. You get the root of C is equal to the root of B plus the root of A. All reciprocals. And this is what's going to help us tremendously to calculate everything that we need to calculate in this question. This formula right here. Okay, so now let's go back to that sum. The sum of all the circles, we have to add their radius. We have to take the reciprocal and then add them. So basically, it's 1 over all the circles in layer 1, layer 0 actually, plus all the circles in layer 1 plus all the circles in layer 2, their radii, plus all the circles in radio 3, and so on, right? Radii 4, 5, and so on, dot, 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 dot. Now you say, well, where's layer 0 and layer 1 and layer 2 and all that? Well, the two big ones, those were layer 0s. So this is layer 0 and this is layer 0. The next one was layer 1. So this is layer 1. The next two are layer 2s. This is layer 2, this is layer 2. And then the other ones that are tangent to those two are 3. This is 3, this is 3, this is 3, and this is 3. And then it just keeps on going like that. So I hope to get a pattern, and this is the section. Let's see, I'll put any kind of pattern here. Okay, so let's do this now. Let's concentrate on this guy first. 1 over R0. Well, we have two R0s. We have this one and this one, and those are basically as follows. 1 over root A plus 1 over root B. Those are the radii. Okay, great. Well, here we go. This is where the formula comes in. That is equal to 1 over root C. So I can put that in 1 over root C. Well, so far it looks like that L0 is the same as 1 over root C. Okay, so far so good. Now let's calculate the next one, which is 1 over R1. Okay, now we got to look at layer 1 circles. Well, there's only one, fortunately. So it's just 1 over root C. Okay, that's good. Well, let's go back and add these. So that's 2 now. And then we got this continuation of this non-stop formula. Okay, what is our tally now? It looked like to me that L1 was the same as L0. All right, so far, if I were to, let's say, make a tally, this is going to be just 1. And that's why we had just 1 here. But then when we add these two, it became 2. And that's why we have a 2 here. Okay, so far so good. Nothing earth-shattering yet, but so far so good. Okay, now let's calculate this one, 1 over R2. So we got this 2 root C. The R2s are here and here. Okay, so to get those, we have to keep in mind that they are the sum of the reciprocals of the two tangent circles. So we have 1 over root A, which is this guy, and then we have this guy. So that's 1 over root C, right? That's how it works in this question. And then we have another layer 2, and it's going to be 1 over root B plus 1 over root C. Right? And then these two guys combine, this one A and this B, to give me 1 over root C. So I'll have 1 over root C and then another one and another one. So that's 3 plus 2 is 5. So it's going to be 5 over root C, and then plus the next one, which will be 1 over R3 root. Okay, so that means L2 was actually this guy, which was 3 LO. So that means when you did the summation of all of those, it became 5. And that's why we have a 5 here. Now let's look at layer 3. And layer 3 is this one, this one, this one, and this one. So I'll just write them down here to kind of see. We got the first layer 3, we got the next layer 3, the next layer 3, and the next layer 3. So in a careful way, let's write out each of them. The first one is 1 over root A plus 1 over root A plus 1 over root C. So that takes care of the first one. The second one is 1 over root A plus 1 over root C plus 1 over root C. The next one is 1 over root c plus 1 over root c plus 1 over root b. And the last one is 1 over root c plus 1 over root b plus 1 over root b. All right, so now we can finally combine them. And of course, this keeps on going with 1 over r4 dot dot dot. So this is 5 over root c. How many root c's do we have? 1, 2, 3, 4, 5, 6. So another 6 over root c. And then we've got 1, 2, 3, and 1, 2, 3. So we have 3 over root a plus 3 over root b. And then we've got this continuation. And this combines to become just 3 over root c. So we've got 3 over root c. And then therefore, this can all be combined into 5 plus 6, 14 over root c. Okay, so at this point, it's going to be very complicated to do any more. So we've got to get a pattern here. So L3, it was these two guys, right? So that was 9 L0. So when you added up everything cumulatively, it became 14, and that's why we have a 14 here. So based on this, I conclude that the pattern is multiples of 3. So L4 is going to be 3 times that, which is 27 L0. L5 will be 3 times that, which is 81 L0. And the final one, because it goes only up until layer 6, is 3 times that, which is 243 L0. So if you were to combine all of these, the 6 layers, let's see, it'll be 14 plus 27 plus 81 plus 243, which is 365. So what that means finally is that that big summation of 1 over r for all circles is 365 times 1 over root c. Okay, now we still haven't figured out 1 over root c. Well, if we remember, 1 over root c was equal to 1 over a plus 1 over b. And they had given us in the question that a was 70 squared and b was 73 squared. So 1 over root c is 1 over 70 plus 1 over 73. 1 over root c. So that would be 70 times plus 73 over 70 times 73. Okay, great. So now we can finally figure this out. So it's going to be 365 times 143 over 70 times 73. And when you reduce that to lowest terms, you get 143 divided by 14. 143 divided by 14 is the answer to this very difficult question. And that is choice D.
Let k be a positive integer. Bernardo and Sylvia take turns writing and erasing numbers on a blackboard as follows. Bernardo starts by writing the smallest perfect square with k plus 1 digits every time Bernardo writes a number. Sylvia erases the last k digits of it. Bernardo then writes the next perfect square. Sylvia erases the last k digits of it. And this process continues until the last two numbers that remain on the board differ by at least 2. Let f at k be the smallest positive integer not written on the board. For example, if k is 1, then the numbers that Bernardo writes are 16, 25, 36, 49, 64, and the numbers shown on the board after Sylvia erases are 1, 2, 3, 4, and 6, thus f at 1 is equal to 5. What is the sum of the digits of f2, f4, plus f6, plus f at 2016? Let's begin. So this is Bernardo, and this is Silvio, or Sylvia. And then here I will put what value of k, here I'll put f at k. So Bernardo, Sylvia, K, and F at K. All right, so let's start discussing this. The first scenario is when K is 1. They give you that in the question, but it's worth talking about. Bernardo is going to write, perfect squares starting with the 1, 2, 3, and so on, right? And eventually he's going to write 49 and then 8 squared, which is 64. And then Sylvia always is going to erase K digits. So removes K digits, always. K in this case is 1. So this one, when you remove the 9, you'll just get a 4. And when here you remove the 4, you'll get a 6. So as you can see, when this table continues with Sylvia, the 5 is missing. So therefore, the value of F at 1 is 5. It's the number that, the smallest number that doesn't appear in either list. Okay, so hopefully that's pretty straightforward. Now let's move up to K equals 2. Okay, so here we have 100 squared, or 100 actually, and then 121, and then you keep on going. The numbers that will be for Sylvia will be 1 and 1. And then eventually what will happen is you'll get up to 59 squared. And 59 squared is 3481. And then when you remove 2, Sylvia, her number becomes 34. And then next one is 60 squared, which is 3600. And when we remove those two numbers, you get 36. So as you can see, there's a 35 missing. And therefore that is the value of F at 2. F at 2 is 35. But we've got to, if possible, I know it's pretty early to do this, kind of get some sort of a pattern. Well, I'll just do what's obvious. This 6 goes to 5, so it's always going to be 1 less. This 36, that means F at 2 is 35, so again, 1 less. All right. And this 60, although you might think, well, how on earth did you get that, is really 50 plus 10 squared, right? 60 squared. And you might say, well, there's no way I would have been able to see why that's important at this stage. Well, hopefully in later stages it will become more obvious. Okay, let's continue. When K is 4, because remember, we have to figure out F at 2, F at 4, F at 6, and so on. So we got to get some sort of a pattern with even values of K, 2, 4, 6, 8, like that. When it's 4, we have 100 squared, which is 10,000 as my initial. When I remove 4 digits, remember you're always removing K digits, you get 1. The next one will be 101 squared, which is 10201. Again, remove 4, you get 1. And then this process continues until you get to 5099 squared, and that is 2599 9801. And when you remove these 4 digits, you get 2599. Sylvia gets. And then the very next one is 5100 squared, and that is 2601000. So when you remove those 4 digits, removing them, you get 2601. So as you can see, the number here is missing, 2600. So that means that F at 4 is 2600. And I am fully aware that that is quite difficult and quite time consuming. So let's put in our stuff that we can get, 1 less. Okay. Now we got to figure out this number here. Well, 5,100 is the same as 5,000 plus 100 squared. So I don't know if you can see a pattern, but hopefully a pattern is kind of emerging. Let's keep going. So I'm going to do 6, and then I'm going to do K, and then I'm going to write in general. So in general, that kind of stuff, because already it's so time consuming. Okay, let's go to 6. I think my pattern is as follows, that you add 2 zeros to the number that begins with the 5, so I'll call that to the 5 number. This guy right here, this is the 5 number. And then you add 1 0 to the number that begins with the letter 1. So I'll call that the 1 number. So you notice here, to go from 50 to 5,000, I had to add 2 zeros. To go from 10 to 100, I had to add 1 0. So I think that my perfect square, my last perfect square that I got to put into these tables on this one is going to be 5,000, add 2 zeros. So that's going to be 5,000,000 plus 100 plus 1 0, so 1,000, all squared. And when you expand that monster, you get 251,001,000,000. And remember, you're removing k digits. K in this case is 6. So when you remove those digits, you get 251,001. And f at k is always 1 less. So f at k, in this case, will be f at 6 we're really talking about. It's going to be 1 less than that number. So that would be 251,000. Right? Okay. All right, let's do one more. And I think one more is enough. Again, use this pattern. And when I do, I will get the last perfect square in this list to be 5,000,000, adding 2 more zeros, right? So 0, 0 plus 1 more 0 to that. So that just becomes 10,000. Square that. Expand that, it's going to be, oh boy, 250,100,100,000, and another 40,000,000. We're removing 8 this time. So let's see here, we're going to remove these guys. And when you do, Sylvia's number becomes 2501,000,001. And to get that, we go 1 less, as before. And therefore, f at 8 is 2501000. All right. I think I'm convinced with that. Okay, so now we have to see any kind of a pattern with these f at k's. Well, this one here is 35, and that one is 25 plus 10, that 35. This one was 2600, and 2600 is 2500 plus 100. The next one was this guy, and 251000, that can be written as 250000 plus 1000. And then this guy here can be written as 250, how many 6 zeros, right? 1, 2, 3, 4, 5, 6 plus 10,000. Okay, so finally I've got my in general. In general, it's going to be f at k will be equal to 25 times 10 to the power of k minus 2 plus 1 times 10 to the power of k over 2. Okay? Now, you don't really need to figure out a formula, but if you can, that's helpful. Okay, so now let's figure out what they want me to figure out, which is a big long sum. And that big long sum is as follows. F at 2 plus f at 4 plus f at 6 plus f at 8, all the way dot, 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 you get the idea, all the way up until f at 2016. Well, breaking it up into these formats helps us add them very nicely, and I'll explain by stacking them one on top of the other. F at 2 is 25 plus 10, right? The next one, f at 4, was 2500 plus 100. The next one, f at 6, was 250000 plus 1000. And then f at 8 was 25000000 plus 10,000. So, and then it just keeps on going like this, plus ... So as you can see, when you add all these up, these guys, these ones, the ones with the 25s in them, will be basically a whole bunch of 25s, 25, 25, 25, like that, ... 25. And then these ones will be a whole bunch of ones, 1, 1, 1, 1, all the way down to a final 0 at the end. And what we have to do is find the sum of the digits. Okay, well, the sum of the digits shouldn't be too big of a problem because there's no carries here. So no carries exist here. So we can just find the sum of the digits of this guy and then add it to the sum of the digits of that guy. Well, this one here looks like it's 1008 25s, right? Because you are adding f at 2, f at 4, f at 6, f at 8, all the way up in 2016. So it's every even one. So it's not 2016. It would be 2016 divided by 2. So that's why it's 1008 25s. And then this one here looks like, again, it's 1008, but this time 1008 ones. Okay, there shouldn't be a problem to add up the sum of those digits. So we've got 1008 of those 2's. This is now the sum of the digits. So sum of digits plus 1008 times those 5's plus 1008 times those 1's. So that's going to be 2016 plus 5040 plus 1008. And that is 8064. 8064 is the answer to this very challenging question, and that would be choice E. The vertices V of a centrally symmetric hexagon in the complex plane are given by these points. For each j between 1 and 12 inclusive, an element zj is chosen from V at random, independently of the other choices. Let P be the product from j from 1 to 12 of zj. Be the product of the 12 numbers selected. What is the probability that P is equal to -1? Well, zj can be any one of these 6. 1, 2, 3, 4, 5, 6. And we can choose any one of those for zj. All right. Well, some of these are similar, so I'm going to put them in two different groups. I'm going to put this and this together, and then the other one I will put in a different group. So, at this point, we have to talk about this in terms of the magnitude. Now, the magnitude of this, if you remember any complex number, a plus bi, if you were to take the magnitude of it, if this is z, then the magnitude is a squared plus b squared under the square root sign, right? So if you took the magnitude of this or this, it gives you root 2. Both of those would give you root 2. That's why I put them in the same category, because their magnitudes are the same. And I'm going to therefore refer to them as A. Now these guys, these 4, in a very similar way, when you take the magnitude, they give the same result. All of them give a half. So I'm going to refer to those guys as B. So that is what we have to work with. Now my product or probability, I think they're calling it product, right? Yeah, not probability. My product is basically this product here of zj from j equals 1 to
12. And they're saying that it's equal to, they want it to be equal to -1. All right, fine. Well, I want to also take the magnitude. If the magnitude is calculated, that's going to help me. And the magnitude of -1, obviously, is 1. So this is the setup of the question. So now let's proceed. Now, in order for us to satisfy this equation right here, we have to basically choose 12 numbers that when you multiply them together, they equal 1. And in particular, the magnitudes equal 1. Okay, well, after you fiddle around with this and think about it, that will happen if you choose 8 A's and 4 B's. Because 8 A's, these are the A's, since each one has a magnitude of 2, root 2, if there's 8 of them, it would be root 2 times root 2 8 times. That's root 2 to the power of 8. And that is 16. If you choose 4 B's, it would be 1/2 times 1/2 times 1/2 times 1/2. So basically 1/2 to the power of 4, which is 1 over 16. And then if you took this and multiplied it by that, it would be 16 times 1 over 16, and that is equal to 1. So that is how you would do this. You would get a product of 1 for the magnitudes. So that means we have to choose 8 A's and 4 B's. But the tricky part about this question is that the 4 B's have to be split up. 3 B's are fine the way they are, but 1 B has to be chosen in a special way. It has to be chosen so that this product is negative. That 1 B will be chosen in a way to give it a negative when you're just multiplying the Z's, not the magnitudes. So just to recap, we're going to choose 8 A's, 4 B's, 3 B's, and 1 B chosen so that the product is -1 rather than 1 or I or -I. All right, so hopefully that makes sense. So here we go. The probability of choosing an A, this guy, is 2 out of 6, right? Because there are 6 numbers, 1, 2, 3, 4, 5, 6, and there was 2 A's of those 6. So 2 out of 6, the probability of choosing an A. And then the probability of choosing a B, well, if you recall, there was 4 of those guys out of this total 6. So this is a third, and this is 2/3. And the probability of choosing that last B that I was discussing over here, this guy, is 1 out of 6. So I want to show you one such example of how the product can be indeed -1. So for the 8 A's, I will choose root 2 I, and since there's 8 of them, we have b to the power of 8. And then for the other b's, I will choose, there's 4 of them, so I will choose 2 to be the 1 plus I type. So that's going to be to the power of 2. And then for the other 2, I will choose the one that is the -1 minus I. And that's to the power of 2. All right, so here we go. The product. Root 2 to the power of 8 is 2 to the power of 4, which is 16. And then we have I to the power of 8. This 1 over 8 and that 1 over 8, since they're both to the power of 2, are 1/8 each. And when you multiply them, you leave 1 over 64. And then now we have to expand this guy, 1 plus I squared. So it's going to be 1 plus 2I plus I squared. And then similarly, we have to expand that guy. And when you expand that, it's 1 plus 2I plus I squared. So 16 over 64 is 1/4. I to the power of 8, I squared is negative 1. So negative 1 to the power of 4 will be just 1. And then this should have been an I squared here. I squared is negative 1, so it cancels with that 1, so you're just left with 2I. And very similarly here, I squared is negative 1, it cancels with that 1, so you're just left with 2I. So 2 times 2 is 4 over 4, and then I squared is negative 1. So there we go. We got negative 1. And that can be done. Here's such an example. All right, so now we have to figure out the probability. Now that I've given you an example, you are convinced that this actually does work. So here we go. Now, the probability of making this from the 12 numbers, remember we're choosing 12, 4 of them have to be B's, right, as stated up here. And the probability of each of those B's is right here, 2 over 3. So 2 over 3. But I'm only going to put 3 because 3 of them are chosen in a way so that you can choose any of them. But 1 has to be chosen in a way so that the product is negative 1. And that one has a slightly different probability. The regular B's have a probability of 2 over thirds. Since there's 3 of them, I put a 3. But the special B, that's chosen so that the product is negative 1 rather than 1I or negative I, that B has a product of just 1 over 6. So that's going to be to the power of 1. And then from the remaining 8, you choose all of those 8 to be my A's. These are my 3 B's. This is my last B or special B. And then those A's have a probability of 1/3. So 1/3 to the power of 8. So there we go. That is my probability. So now we have to simplify these numbers. The 12 choose 4 will be 12 times 11 times 10 times 9 divided by 4 times 3 times 2 times 1. And then we have 2 to the power of 3, 3 to the power of 3. Then we have 1 over 6. And then we have 1 over 3 to the power of 8. And then when this is all said and done and you cancel out all the relevant terms, all you're left with is 2 to the power of 2 times 5 times 11 over 3 to the power of 10. 2 to the power of 2, 5, 11, and 3 to the power of 10. That would mean number 25, the answer is E. First, let's start off with a simple example to kind of illustrate what this question is talking about. Let's say n is 3, and therefore A would be 3 digits, and all the digits are equal to A. So it would be A. Similarly, B would be 3 digits with all being B. C, however, is 2n digits, so 6 digits with all its digits being C, like this. And they're basically saying when you do that, this has got to hold true. So this is, of course, C3, B3, and A3. So they're saying that whatever happens, once you get these numbers, you plug them in, and this holds true for 2 values of n. So I'm just going to give you an example. Let's say B is equal to 5. Okay, this is just an example. That means B3 is 5, 5, 5, right? So the trick to this question is trying to figure out a very cool way of manipulating these numbers. So 5, 5, 5, I'm going to write as follows. If you divide this by 5, obviously, you would get 1, 1, 1. Now, what is 1, 1, 1? I like the 5, I'll keep that. 111 is really 999 divided by 9. And 999 is really 10 to the power of 3 minus 1. So this is basically what we want to do. We want to take the number and put it in this form.
That's challenging. I understand.
So in general, if we were to sort of make a general formula, it would be that Bn would be B times 10 to the power of n minus 1 over 9. If you notice, this one, of course, I had given specific values for n and for b. But in this one, this is general. N is just n and b is just b. Okay, so now we can go to the question. Now that we have a strategy. So let's look at that one. So we've got c to the n minus b to the n is equal to a to the n all squared. C to the n would be, according to this formula, c times 10 to the power of 2n minus 1 over 9. B to the n is b times 10 to the power of n minus 1 over 9. And then a to the n is a times 10 to the n minus 1 over 9 all squared. Correct? All right. So if you're convinced of that, let's move forward here. So at this point, let's do a little bit of expansion, not too much. C 10 to the n minus 1 and 10 to the n plus 1, and that's going to be over 9. B, this is just going to be pretty much the same thing. Not much I can do there. This one, a squared 10 to the n minus 1 all squared. And then 9, don't forget to square that one. It's going to be 81. Now at this point, we can divide by 10 to the n minus 1 because that appears with everything. And when I do, it's going to be c to the 9, just one of these 10 to the n plus 1, because 10 to the n minus 1 will disappear. And then from here, it'll be just b over 9 because the 10 to the n minus 1 disappears. And then here it'll be a squared over 81, and then just one of those will remain 10 to the n minus 1. Okay. Now let's multiply through by 81 to get rid of the fractions, and when we do, we get 9c 10 to the n plus 1 minus 9b, and then a squared 10 to the n minus 1. Okay, so we're making some progress here. At this point, we want to expand and collect like terms as best as we can. So let's do that. This is going to be 9c 10 to the n plus 9c minus 9b is equal to a squared 10 to the n minus a squared. Let's put the 10 to the n's on one side and factor. When you do, you get 9c minus a squared. And then we have 9 on the other side. If I put everything else on the other side, it would be 9b minus 9c, and I believe just alone minus a squared. Okay, great. Now, here is the part of the question. This must hold true for two different values of n. And we can call those n1 and n2. So basically it means that 9c minus a squared times 10 to the n1 is going to be 9b minus 9c minus a squared. And 9c minus a squared to the 10 to the power of n2 is also going to be equal to 9b minus 9c minus a squared, right? Because both of them have to be equivalent. You're going to have this equation holding true for two values of n. So I'll call those equations 1 and 2. And then at this point, what I'm going to do is subtract them. 1 minus 2. So 1 minus 2 would give me 9c minus a squared 10 to the n1 minus 10 to the n2. And on the other side, it basically becomes 0. Okay. So the only way this is going to work is if this is equal to 0. Because this can't be 0 because n1 and n2 are two different numbers. So that means I conclude that 9c minus a squared is equal to 0. And if that is the case, and you plug that back into 1, then the left side becomes 0. So that means this is equal to 0. So that 9b minus 9c minus a squared is 0. And these two will help us solve for a, b, and c, I hope. From this one, we get 9c is equal to a squared, and therefore c is equal to a squared over 9, which is a over 3 all squared. From this one, let's see what we can get here. We get 9b minus 9c minus a squared. So 9c is equal to a squared, this guy, so I can just put a squared minus a squared is equal to 0. So that means 9b is equal to 2a squared. And 9b, therefore, a squared is 9c, so 2 times 9c, right, from this right here. So that means b is equal to 2c. Yeah, that's it. Okay, so now I think we're ready to figure out a, b, and c. A, b, and c. Well, from here, these are all integers, so a obviously is divisible by 3. So a can only be either 3, 6, or 9, because remember, each of those are digits, so they're only between 1 and 9. If a is 3, I think I can immediately figure out c. So if a was 3, c would be 1. If a was 6, c would be 4. And a was 9, c would be 9 also. Okay, now let's figure out the corresponding values of b using that formula. b is just 2 times c, so 2, 8, and 18. Well, this one is invalid because b has to be a digit, right? So this one here, that doesn't work. So I guess the only ones that work are that order triple and that order triple. So now we have to figure out the value of a plus b plus c. Okay, from this guy right here, a plus b plus c is 6. And from this one, it is 18. And we have to choose the largest. So the largest obviously is 18. And therefore, going back, what is the greatest possible value of a plus b plus c for which there are at least 2 values of n such that cn minus bn is equal to an squared? We just figured out that answer is 18. And therefore, number 25, the answer is D. Let triangle A0, B0, C0 be a triangle whose angle measures are exactly 59.999, 60, and 60.001. For each positive integer n, define an to be the foot of the altitude from an-1 to the line bn-1, cn-1. Likewise, define bn to be the foot of the altitude from bn-1 to the line an-1, cn-1, and cn to be the foot of the altitude from cn-1 to the line an-1, bn-1. What is the least positive integer n for which the triangle an, bn, cn is obtuse? Obtuse meaning that one of the angles is greater than 90 degrees. All right, so let's draw what is an equilateral triangle, because it's very, very close to being an equilateral triangle when you first start out. If you look at the angles, they're very close to 60, 60, 60. Not exactly, but very close. So now let's work with this. Let's label it first A0, B0, and C0. And then
the definition entirely based on what's written in the question is that you're going to draw altitudes. So first let's draw this altitude. That's of course a right angle. And then draw another altitude that hits there, right angle. And another one from there to the other side, right angle. And when you do that, you get A1 here, B1 here, and C1 here. And they're saying that together, those form a triangle. So this is the triangle it forms. And this is the first one, A1, B1, C1. And they want you to figure out the angles, and then eventually there's going to be a triangle where one angle is greater than 90 degrees. Okay? So there is a little bit of a technique, and that is making these cyclic. So I'll just draw in the first circle to illustrate how you make it a cyclic quadrilateral. So there you go. I've taken this quadrilateral right here, and I put it entirely inside a circle to illustrate that it's a cyclic quadrilateral. And then now, if you notice, this angle, it originates from those 2 points on the circle. And so does this angle. So because they originate from the same 2 points that are on the circle, the same arc, I guess, on the circle, those two angles will be the same. So if this is theta 1, this will also be theta 1 right here. Okay, so let's do the same thing, but this time on another circle or another quadrilateral. And there we go. Here's another one. This time I've taken this quadrilateral and I've inscribed it into a circle. So in the same way, if I look at this angle, it starts from these 2 points, and then I take the same 2 points and create another angle. And when I do, those two angles will be the same. So if this is theta 2, this will also be theta 2. So that's theta 2, and that's theta 2. This is theta 1, and that's theta 1. All right, so now let's start calculating some of the A1, B1, and all that stuff. So this was 90 degrees, right? So this is also 90 degrees here. So that means that if you look at this triangle right here, theta 1 is equal to 90 minus angle A0. This is angle A0. And in a very similar way, if you look at that triangle, that's also a right triangle. This is a right angle. So theta 2 is also equal to 90 minus A0. So if we add them, theta 1 plus theta 2, they would be 90 minus A0 plus 90 minus A0, so it's 180 minus 2A0. Okay, so now we're ready for A1, B1, and C1. A1, that angle. And A1, that angle, is right here. It basically is equal to theta 1 plus theta 2. And that is 180 minus 2A0. Well, they've given us the angles, and so let's just assign them. A0 I will call 59.999. B0 I guess I can just call 60. And then C0 I can call the other one 60.001, like that. Okay, so in a very similar way, B1 would be 180 minus 2B0. And if you do that math with B0 equal to 60, that's just 60. And then this one I can actually get a numerical value since A0 I've assigned this. 180 minus 2 times 59.999, it would give me 60.002. And finally C1 would be 180 minus 2C0, since it would have pretty much the same pattern of calculation, And C0 is 60.001, so that would give me 59.998. Okay, and then you just keep going. Again, A2, it would be the same principle, 180 minus 2A1. And if you do that, you will get 59.996. B2, well, that's just going to be 180 minus 2 times B1, and that's just going to be 60. And then C2 will be 180 minus 2C1. And if you do that math, you will get 60.004. Okay, so at this point, I hope you can see some sort of a pattern. If you can't, that's okay. I will just make a little table here. We've got n, which it could be 1 or 2 and so on. And then we've got our angles. So for example, for 1, it's A1, B1, and C1. And then what is the largest angle? Because we want eventually to get an angle that's greater than 90. All right, so let's look at this and see. It initially may seem like this would take absolutely forever, but if you look at the answer choices, it's actually not that bad, the highest being 15. Because we're going up by such small values that it may seem that it would take, hundreds of iterations to get above 90. But it obviously can be done in 15 or less. So let's see. For when n is 1, the largest angle was this guy. So 60.02. 002, I should say. When n is 2, we'd have A2, B2, and C2. And as we calculated here, the largest was this guy, 60.004. And it looks like it's doubling. And I'm confident of that because when n was 0, we had A0, B0, C0, and the largest was, well, the largest of A0, B0, and C0 was this guy, 60.001. So 60.001. So as you can see, it is doubling. So for A3, B3, and C3, it would just be 60.008. What's doubling actually is not the full number. It just seems to be that part of the number that seems to be doubling. Okay, so let's just keep going. I'll just do it really quickly. So this is going to be 60.016. When it's 5, it'll be 60.032. When it's 6, it will be 60.064. When it's 7, it will be 60.128. It seems like you're never going to get to 90 within 15, but it tends to, the magic happens very quickly. Kind of reminds me of compound interest when you're investing. So number 9, 60.5. Sorry, this was 256. Now we have 512. Number 10. Now we're getting above 61. Ooh, okay, a little bit of progress. 11 would be 62.048. 12 would be 64.096. 13, 68.192. 14, 76.384. And the 15th is 92.768. There you go. AN, when n is 15, gives you an angle that is greater than 90. So, very interesting question. Number 25, the answer is E. The number A is equal to P over Q, where P and Q are relatively prime positive integers, has the property that the sum of all real numbers, x satisfying x bracket times x symbol, is equal to A dot multiplied by x squared. and that is equal to 420, where x bracket denotes the greatest integer less than or equal to x, and x symbol is equal to x minus x bracket, denotes the fractional part of x. What is p plus q? All right, let's explain this question first. Let's say we have x is equal to 7.32. Then that means x bracket is the greatest integer less than or equal to that, which would be 7. And then this, I guess that's also a bracket of some sort. It would be the fractional part. So the fractional part is 0.32. So that is pretty much what they mean by that. Okay, so we want this to equal that. So obviously there's going to be some sort of a graphical element to this. So let's attempt to draw this graph. So first I'm going to draw the graph of y is equal to bracket x times symbol x. All right, when x is 0, this is x and this is y. When x is 0, we have 0. Now I'm going to draw this in segments of integers 1, 2, 3, and 4, like that. Now, let's just brainstorm this. When x is, say, 0.5, then what do we have? We'd have y is equal to 0 times 0.5. Well, that's just 0. And then any number before 1, it's also going to give you 0. So if this is 1, anytime you get to a number before 1, it's just going to be a flat line like that. And then now when we get to 1, what is it? Well, we have, when x is 1, we have the bracket x would be 1, but the fractional part is 0. So again, we get 0. So it still stays at 0 here. But then as we get to like 1.1, then it starts to rise. So 1.1 for x would give me 1, but the fractional part would be 0.1. So now we get a little bit of a rise, and then it just keeps rising until we get to before 2. It actually will get up to 1. So it'll be right here, but it won't be exactly 1. It'll just be up to 1. So for example, if x was, say, 1.99, right? That's right before we get to 2. Then this would become y is equal to 1, because that's 1.99 bracket would be 1, and the fractional part would be 0.99. So as you can see, it would be 0.99, and that matches up with what I drew. But then once we get to 2, what happens? Well, once we get to 2, we get y is equal to 2 times 0, because the fractional part of 2 is 0. So then we come right back down to 0 again, like there. And then I don't want to exhaust you by walking you through this. I think you kind of get the idea. If you keep going like this, when you graph the next one, it goes up to 2. So approximately here. That line like that. Until we get to that point, and then it's not going to include that, and that's 2. And like I said, you can use smaller numbers in the interval like 2.2, 2.5, 2.7, all the way up to 2.99 to kind of get an idea of how this works. And then I'll just do one more. So 4, by now I think you have an idea what this is going to look like. It will just go up to 3 on the y-axis, which is approximately here. Yeah, approximately there. And again, it will be a circle, which indicates that it doesn't actually get to that point, but it gets sufficiently close to it. So this is sort of the graph of that. Now what about the graph of this? Y is equal to, let's use a different color, ax squared. Well, y equals x squared, that's easy. That's just a parabola like that. What about when you multiply it by a? Well, based on what they've told me, it looks like a is a fraction that's less than 1, right? So that means this graph will flatten out when you multiply it by something less than 1 when the coefficient is less than 1. So that means, I'm not sure, but something like this, right? And then similarly on the other side. Now notice, I just concentrated on quadrant number 1 because quadrant number 1 is where all the action is. Nothing else happens in this other quadrant because of the nature of this equation. So that's how we plot this. So we are basically looking for these intersection points. And each of those intersection points represents an x that satisfies that equation. And then I have to add them all up. And when I add them all up, I get 420. Because eventually what will happen is that this parabola will exceed the lines. So like one line would just be like this, and the parabola would never touch it. So there's only a finite number of lines that make the parabola and the lines touch. And that's why there's a finite number with regard to the sum of the intersection points. All right, so we are set. Well, not quite. Still have a ways to go, but at least we have the foundation. Okay, I want to do it in a very, very straightforward way. So this first line right here that I just drew right there, that obviously is a line that has the point 1, 0 on it, right here. And that line you can easily figure out has a slope of rise over run, which is 1 over 1. Slope is equal to 1. I'm using m to represent my slope. The second line has the point 2, 0, which is right here. And that has a slope rise over run of 2 over 1, so that slope is 2. Second line, this one here, has the point 3, 0 on it, right here. And it has a slope of 3 over 1, so m is 3. So very quickly, we can get the equations of these lines. So y is equal to mx plus b, so m is 1, so x plus b. When I substitute that point, I can get the value for b. When x is 1, y will be 0. So that means 0 is equal to 1 plus b. b is equal to negative 1. So that equation is y is equal to x minus 1. All right. And then, in a very similar way, I won't walk you through it because I'm certain you know how to figure out the equation of a line. This is going to be y is equal to 2x minus 4. And this line is y is equal to 3x minus 9. I think you might already be seeing a pattern. Now, I'm interested in the intersection point. The intersection of what? This parabola, which is y is equal to ax squared, with each of these lines. So the first intersection point was when ax squared is equal to the first line, like that. Okay, let's put everything on one side, and that gives me 0. I can easily use a quadratic to figure this out. X will be minus b plus or minus the square root of b squared minus 4ac all over 2a. And that looks like 1 plus or minus 1 minus 4a all over 2a. Okay, that's pretty straightforward. Let's do 2 more. Let's just do those 2 lines. So the next one is ax squared is equal to 2x minus 4 this time. Put everything on one side. Ax squared is minus 2x plus 4 is equal to 0. So now again, using the quadratic, we get x is equal to 2 plus or minus the square root of 2 squared minus 4ac all over 2a. And this gives me x is equal to 2 plus or minus, I'm going to be able to factor out a 4, and that'll give me a 2 when I bring it out of the radical, and that'll just leave me with 1 minus 4a all over 2a. So that looks like exactly like this. It's just there's a 2 out front. So 2, 1 plus or minus 1 minus 4a over 2a. Okay, one more involving that line. So same thing. We've got ax squared
is equal to 3x minus 9 this time. So same thing, ax squared minus 3x plus 9 is equal to 0. So x is equal to 3 plus or minus 3 squared minus 4a times 9 all over 2a. And this will give me x is equal to, I can factor out the 3 this time. So 3 plus or minus, factor out the 9, and then if you bring it out of the radical, it'll be a 3. Then again, I get 1 minus 4a all over 2a. So this is x is equal to 3 times 1 plus or minus 1 minus 4a root over 2a. All right, so I hope you see a pattern. The first root, it was just this by itself. Then it was 2 times that. Then it was 3 times that. And it will just keep going like that. And then note something very important, that each of these x values, so for example, this is the first one, right? Each of those x values, and I'll write it in red because this is important, is going to be between 2 integers, right? So, for example, the first x is right here, and that x is our first x right here. So I'll call that just x1. And x1 has to be somewhere between 1 and 2. So we'll put that in there. It's going to be between 1 and 2. The next x, which is the next root, is right there. I'll call that x2. So that's x2. And that has to be obviously between 2 and 3. So it's going to be between 2 and 3. And then the third root, which is right there, I call that x3, which is down here, call that x3. That guy has got to be between 3 and 4. So it looks to me that x to the m is between m and m plus 1. So that's an important point that we will use a little bit later. All right, so let's proceed now to the next part of the question. We have a general sort of understanding of what x is. X to the m looks like m times 1 plus or minus 1 minus 4a all over 2a. And you can see that pattern here, you can see that pattern here, and you can see that pattern here. This one right here. All right, so all that hard work to get basically this. But there's a little bit of confusion because you have 2 roots, plus or minus. Why is there 2 roots? And which one do I choose? Well, let's say we have these graphs, right? Now, these lines abbreviated, you remember they stopped, but our equations don't stop. Our equations go on forever, right? The equations of the lines go on forever. So what happens eventually is that you have these parabolas that eventually will come and sometime in the very, very distant future cross again. So you notice how it crossed once and it crossed twice like that? That's why there's 2 roots. So we want the smaller one because eventually we have a finite number. So we're not going to actually have to worry about the second root. And that's because our particular a is so flat that it doesn't do that. So we want the smaller of the 2 roots. So the smaller of the 2 roots would obviously be the one that is the negative. So here's a little bit more of an explanation. Choose the negative, the smaller of the 2 roots, because that is the value of x that the graph meets first. All right, so we are set. So now we want the sum, because we are told that the sum of all the roots is 420. So that's going to be 1 times 1 minus 1 minus 4a over 2a. And then we have 2 times the same thing, 1 minus 4a all over 2a. And then we have 3 times 1 minus 4a, and so on, right? You get the point. But my question is, how far do I keep going here? Until when? If I knew until when, I could figure this out, because I only have one variable, and that's a. So now I've got to kind of figure this out as to how far this goes. Because once I do, then it's a piece of cake, because I just figure out, factor rather, this 1 minus this whole thing, 1 minus the square root of 1 minus 4a all over 2a. And once you factor that out, you'll see, then you just have a bunch of consecutive numbers, until some value. Because remember, there's a finite number. And the proof of that is that the sum is finite. If it was infinite, then the sum would be infinite. Okay, so I've got to concentrate on figuring out that n now. Or, I'm just going to call it m, since I've been calling it m so far. I'm just used to n. Now, you all know the sum of that. That's going to be m times m plus 1 all over 2. And then you've got this thing hanging over our heads right here. And that is equal to 420. Okay. Now, as promised, I'm going to use this very important inequality to help me, that xm is between m and m plus 1. So just put that on the side there, that xm is between m plus 1 and m, like that. Okay, now before I can use that, I've got to manipulate this a little bit. Let's multiply through by 2 and make it 840. And let's divide through by m plus 1, like that. And then all I will be left with is just an m and then this weird equation. Okay, now this is part I have to discuss. Look at this right here. This is of the form of a solution, right? Because all of our solutions were of that form. Some m multiplied by this term. If you notice, x1 was just, 1 multiplied by that term. x2 was 2 multiplied by that term. x3 was 3 multiplied by that term. And then we concluded that we have to you choose the negative only, and therefore our terms became like this. As you can see, 1 multiplied by that term, 2 multiplied by that term, and 3 multiplied by that term. And that term is right here. So this is basically in the same form as a solution. So some x. And we know that all x's are between m and m plus 1. So we can safely say that this is between m and m plus 1. But that is equal to this. So this is between m and m plus 1. So that means that 840 over m plus 1 is between m plus 1 and m. All right, so I hope I was clear on that. Now I can use this to figure out what is m. And I think I'll just use this part of it, that part of the inequality. So m times m plus 1 is going to be less than or equal to 840. Now, m times m plus 1, I'm not going to use a quadratic, just approximate. This is sort of like m squared, right? M times m. So m squared is less than 840. So that's what's the square root of 840, approximately? Well, 30 squared is 900, 29 squared is 841, right? So 29 is pretty close. So let's say if m is 29, what happens? This becomes 29 times 30, and 29 times 30 is 870. Okay, so that's not less than or equal to. So I'm going to then try m equals 28. If that is the case, then I get 28 times 29, for this, and that is 812. So that is indeed less than 840. So m has to be 28. And there you go. I just got that. And that is exactly what I wanted. So m is 28. So now I'm ready to solve this. All right, we are ready to solve this. This right here, we know. We can easily do that. We know that formula. It's 28 times 29 divided by 2. And that's going to be 420, and this is the same. So cross multiply, and this becomes 840. 28 times 29 is 812, and that goes in the bottom. This fraction reduces actually to 30 over 29, and then now I can cross multiply. So it's going to be 60a is equal to 29 minus 29, square root of 1 minus 4a. And then let's put the radical on just one side. So that would make it 29, 1 minus 4a like this. And on the other side, it would be 29 minus 60a. And then square both sides. Obviously, we want to get rid of that radical. So 29 squared, 1 minus 4a. And then this is going to be 29 squared minus 2 times 29 times 60a plus 60 squared a squared. All right, moving right along. Now I think I can multiply this out and collect like terms and put it all on one side. So let's see here. It'll be 60 squared a squared. And then I've got minus 2 times 29 times 60a. And then that's going to be, bring it over, it'll be plus. So plus 29 squared times 4a. And then the numbers by themselves are 29 squared and then minus 29 squared. Okay, that's nice. So that means I can factor out an a. Since this cancels out, the only thing I'm left with is just a's. So I can factor out an a. I get 60 squared a minus 2 times 29 times 60 plus 29 squared times 4. All right. So now that a goes, I can just, because a is not 0, so I can just get rid of that a. So 0 is equal to this, which is 3600a minus 3480, and that's plus 3364. All right, so that means 3600a. If you add those and put them on the other side, it will be 116, and therefore a is equal to 116 over 3600. And in lowest terms, a would be 29 over 900. And that is our P over Q, finally. And therefore, P plus Q, 29 plus 900, which is 929. There we go. Whew, that was a very hard question. I have no idea how people are able to do these questions in 3 minutes on a math contest. Number 25, the answer is 929, which is choice C. Let d at n denote the number of positive integers that divide n, including 1 and n. For example, d at 1 is 1, d at 2 is 2, and d at 12 is 6. This function is known as the divisor function. Let f at n equal d at n over the cube root of n. There is a unique positive integer capital N such that f at capital N is greater than f at n for all positive integers small n not equal to big N. What is the sum of the digits of n? Well, I'd like to start off with a primer to explain this. I want to give you a quick way of figuring out the number of divisors. So if I told you any number, you should be able to figure it out quickly. So f at 12, which they already gave you, and in particular, let's just start off with the d part. So the number of divisors, right? Well, first what you do is you break up 12 into its prime factors. So 12 is really 2 squared times 3 to the power of 1. And therefore, that would be as follows. You take this exponent and you add 1. And then you take this exponent and you add 1. And that you multiply. So it would be 3 times 2, which is 6. So therefore, that is 6. And that's why that's 6. Now, what if you have, say, d at 7? Well, d at 7 is just a prime number. It's just 7 to the power of 1. So the number of divisors, you take that exponent, and you always just add 1. And that's it. So that's 2. What if I said d to the 4? Well, d to the 4 is d2 squared. So again, you take that exponent, and you add 1. So that's just 3. So that's a quick way of figuring out the d's. So now what I'm going to do is just kind of show you the first few on the side here. So d at 1 and d at 2, and then we'll do the f's. So here we go. So d at 1, well, that's already given as 1. D at 2, that is given as 2. Now d at 3, remember that's 3 to the 1, so you take the exponent 1, add 1, so that would be 2. Generally speaking, any individual prime number, the answer would be 2. D at 4, well, 4 is equivalent to 2 squared, so that 2 is the exponent, add 1, you get 3. D to the 5, well, that's a prime, that's going to be 2. D at 6, 6 is 2 times 3, right? 2 to the power of 1, 3 to the power of 1, so it would really be 1 plus 1, which is 2, times 1 plus 1, which is 2, so that's going to be 4. And you get the hang of it. D at 7 would be 2. D at 8, well, this is 2 to the power of 3. So this time, exponent is 3, add 1, you get 4. And then d to the power of 9, that's 3 squared, so that's going to be 2 plus 1, which is 3. And then d to the power of 10, that is 2 times 5, and that's going to be 2 times 2, which is 4. And then d to the power of 11, well, that's just an individual prime, so that's 2. And so on. D12 we just did was 6. Okay, so I did it in an exhausting way because I wanted you to get it. Now f, we have to turn our attention to this guy. F at 1, well, that's just the answer for d and then over root, cube root of n. That's pretty straightforward. So that's just going to be 1 over 1, which is 1 in that case. F at 2, it looks like it'll be 2 over cube root of 2. And then f at 3 looks like it will be 2 over the cube root of 3. And so on. F at 4 is going to be 3 over the cube root of 4. And so on, right? You guys get the hang of it. Okay. So all that I just wanted to do just to explain it. Now let's begin with the actual question, because otherwise I think it might be a little too abstract. Okay, so the first thing we have to recognize that's going to make our life very helpful is f at n is going to be obtained or possible to obtain by doing a multiplication. So for example, if n is equal to a times b, f at n will be equal to f at a times f at b. And that's something that's very important to recognize. So for example, let's say n was 12. Well, 12, as you are well aware, is 3 times 4. Well, let's see if this works out. F at 12, does it indeed equal f at 3 times f at 4? Well, f at 12 is equal to 6 over the cube root of 12, if I did that properly. F at 3, I think I already did f at 3, that is 2 over the cube root of 3. And f at 4, I think I already did that as well. That is 3 over the cube root of 4. So does this match up? It sure does, because the right side would become 6 over the cube root of 12. So this is something that is very crucial to the question. Okay, so now what do we do? Now we have to recognize that what they actually want is the following. They want you to figure out some f at big N
so that it is the largest possible, meaning every other f at n would be smaller. So in being consistent with what we've already done, I'm going to make n into a prime factor. So 2 to the power of something, 3 to the power of something, 5 to the power of something, and so on. But when I first saw this, I thought, well, isn't this just going to go on forever? How do I know what's the largest possible? What if it's a million? What if it's a trillion? Well, my hunch is that we have to look at each of these individually and then see if these are increasing indefinitely, or if they are decreasing, or if they're less than 1. And let me explain. We have to look at each of these individually, and hopefully we will sooner rather than later get a maximum. And then we'll stick that in. So it could be 2 to the power of 1, or 2 to the power of 2, or 2 to the power of 3, whatever. And then similarly, we'd have to do that for all of these, for 3, for 5, for 7, and so on. Next prime factor would be, of course, 11, and then 13, and then ... But I think eventually what will happen is that some of these will be less than 1, always. So if they're less than 1, then we don't want to include them, because if we include them, that would make our f at n value decline. So without talking about this anymore, let's just do it. So here we go. Let's start with powers of 2. And in particular, we're going to do f at 2 first, of course. So that is going to be 2 over the cube root of 2. And the challenging part is you're not allowed to use a calculator, so you have to really estimate this. Okay, so I'm going to write it as 1.6 as an estimate. And then f at 2, the next power, 2 to the power of 2, that was 2 to the power 1. That is, by now, hopefully you're an expert, 2 to the power of 2, that's going to be 3 over root 4, the cube root, that is, and that is approximately 1.9. Okay, then we got the next power, 2 to the power of 3. That's going to be 4 over the cube root of 8. Well, the cube root of 8 is 2, so 4 over 2, that's going to give you 2. Now let's go to 2 to the power of 4. That's going to be 5 over the cube root of 16, right? And that is approximately 1.98. So as you can see, it starts going down now. So therefore the maximum looks like this guy. So that means for A, my maximum looks like it will be 3. All right. That's the maximum I will be able to get for f at n when I'm using 2. So by the same criteria or same pattern, let's do 3. 3 to the power of 1. That's going to be 3 over root 3, cube root of 3, and that is approximately 1.4. Sorry, that should have been a 2 there. And then 3 to the power of 2, that's going to be a 3 over the cube root of 9, and that is approximately 1.44. And then 3 to the power of 3, well, that's 4 over the cube root of 27, and that's just going to be 4 over 3, which is 1.33. So as you can see, it starts going down, so therefore the maximum for this guy is there. So therefore that B is going to be a 2. Okay, let's keep going here. All right, f at 5 to the power of 1, that's going to be 2 over the cube root of 5, and that is 1.2 approximately. And therefore the next one, f at 5 to the power of 2, is 3 over the cube root of 25, and that is approximately 1.0. So as you can see, it's going down. So that means this is the biggest one. So that means the C must be a 1. Let's keep going here. F at 7 to the power of 1, that's going to be 2 over cube root of 7, and that is approximately 1.04. And then f at 7 to the power of 2, that's going to be 3 over the cube root of 49, and that is approximately 0.82. So as you can see, it's going down. So the maximum happens when you have 7 to the power of 1, so that d must be a 1. Oh boy, getting tired here. All right, keep going. 11, f at 11 to the power of 1. So that's 2 over the cube root of 11, and that is 0.9. Ooh. Okay, this is what I had anticipated. I even wrote that there. So we don't want to include these because if you do, it will, instead of making it bigger, it will make it smaller. Let's just do one more, 11 to the power of 2. That's going to be 3 over the cube root of 121, and that is 0.6. So indeed, those are all going to be less than 1. So this e was 0. We don't want that. And then let's just do one more, prime 13. That's going to be 2 over the cube root of 13, and that is 0.85 approximately. And then f at 13 squared would be 3 over 169 cube root, and that is 0.5, I think. So as you can see, these are always going to be less than 1. And I think the pattern for any prime greater than 13 will also be that it'll be less than 1. So less than 1, dot, dot, dot. So for 13, obviously, it'd be 0. So I conclude my n is 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 1 times 7 to the power of 1. And therefore, if you multiply all those out, is 2520. The sum of the digits of n is 2 plus 5 plus 2, and that is equal to 9. 9 is the answer to this very challenging question. I have no idea how people can do this without a calculator, and especially considering that calculators are not allowed on this math contest. In any case, number 25, the answer was 9, which is choice E.